4 billion years ago, Earth was not blue and familiar. It was a restless young planet under a strange sky, with iron-rich oceans, raw black crust, falling debris from space, and the first quiet signs of life spreading as microbial films along ancient shores. The Archean Eon is where our planet begins to remember itself, where water stays, stone survives, continents gather, and oxygen first appears as a tiny waste product that will one day change everything. Welcome to Calm Earth Science. If this kind of deep time journey helps you relax, learn, or drift into a slower state of mind, please like the video, subscribe to the channel, and share it with someone who loves Earth's ancient story. Thank you for spending your time here. What time is it where you're listening, and from what part of the world? Leave a comment below. Now, let's step back into Earth's Archean dawn. The Archean begins at a boundary that is easier to name than to see. Around 4 billion years ago, Earth is no longer the fully molten body of its earliest infancy, but it is not yet a familiar planet. It has a crust, yet that crust is thin, restless, and repeatedly broken by heat from below and violence from above. It has water on its surface, but the oceans are young, chemically unusual, and surrounded by air that no animal could breathe. It has a moon, already moving slowly away after its violent origin, and that companion shapes tides beneath a sky still crowded by the leftovers of planet formation. The planet has crossed out of the Hadean, the hidden interval whose rocks have mostly vanished, and entered an eon where the record begins to hold more fragments. Even so, the first impression is not stability. It is persistence under pressure. Earth is becoming a place where surface environments can last long enough to matter, but nothing about that endurance is secure. The interior remains hot from formation, from radioactive decay, and from the long aftermath of impacts. Volcanism is one of the main languages of the planet. Basaltic lava spreads across young crust. Gases rise from vents and fissures, and the early atmosphere thickens through repeated outgassing. Carbon dioxide, water vapor, nitrogen, methane, sulfur gases, and other compounds surround the planet in a mixture far removed from later air. Oxygen, in the form needed for breathing, is almost absent. The air is likely hazy, dense in greenhouse gases, and strongly connected to the chemistry of volcanoes, oceans, and sunlight. Above it, the sun shines with less power than it does in later ages, yet Earth does not freeze. Greenhouse warmth fills part of that gap, trapping heat around a planet that is still cooling from its own beginning. This is one of the first quiet tensions of the Archean. The young sun is dimmer, the surface is hot, the air is alien. And the oceans must remain liquid if the later story of life is to have any place to unfold. The planet solves this problem not by design, but by balance heat from within. Greenhouse gases above, and water moving across a surface still being remade. The result is neither a paradise nor a dead stone. It is a working planet, harsh but open to change. The surface at the opening of the Archean is difficult to reconstruct, because Earth is unusually good at destroying its own past, unlike the Moon, where ancient scars can remain exposed for billions of years. Earth recycles, its crust bends, sinks, melts, erupts, erodes, and is buried. Oceans alter rock, heat erases minerals. Tectonic motion carries fragments downward or folds them into new mountain roots. The rocks that survive from this early time are rare not because little happened, but because too much happened afterward. A complete landscape cannot be recovered. Instead, the Archean threshold appears through remnants, ancient mineral grains, battered crustal blocks, chemical signatures, and the oldest surviving terrains that escape total erasure. These fragments do not give a full map, but they show that the world had already begun to organize itself into lasting parts. There are hints of continental material, not continents in the modern sense, but buoyant pieces of crust that resist sinking more effectively than ordinary oceanic basalt. There are signs of oceans, not merely temporary pools, but broad bodies of water interacting with rock at planetary scale. There is evidence that Earth is entering a new pattern, one in which the surface is not only cooling, but differentiating into environments with their own histories. Rock and water are no longer just consequences of formation. They are active participants in a system. Rain falls through an atmosphere rich in volcanic gases. Water gathers in low regions of a still uneven surface. Waves, tides, and chemical reactions attack fresh lava. Minerals dissolve, precipitate, and alter. Heat rising from the interior drives circulation through fractured crust, creating places where water can pass through hot rock and return changed. Each action seems small against the scale of an eon, but together they make the surface more complex. A young planet once dominated by global melting is now broken into environments. Some are volcanic and violent, some are submerged and dark, some are shallow, mineral-rich, and exposed to sunlight. Some are repeatedly destroyed and renewed. The important change is not that Earth becomes calm. It is that Earth becomes varied. Variation creates opportunity. It allows chemistry to happen in different ways at different boundaries between ocean and crust, between atmosphere and water, between hot vents and cooler seas, between newly erupted rock and the first sediments laid across it. The Archean threshold is therefore a physical transition before it is a biological one. It prepares the architecture in which life may later become visible. The impact environment remains part of that architecture. The solar system has not yet settled into the quieter rhythm of later time. Debris still crosses Earth's orbit, and large collisions can release enough energy to boil seas locally, fracture crust, and cover wide regions with molten rock or vaporized material. Some impactors bring destruction, some may also bring water and carbon-bearing compounds. This same event can erase a surface and enrich it. That dual role gives the early Archean one of its most difficult shapes. It is not a simple story of improvement from chaos into order. The forces that make the planet dangerous may also help build the inventory from which later environments develop. A comet striking young Earth can deliver volatile material while blasting open a wound in the crust. An asteroid impact can reset a region while exposing fresh minerals to ocean water. The distinction between catastrophe and contribution is not always clean when the planet is still assembling its conditions. Earth is habitable only in a limited and unstable meaning of the word. It has liquid water, it has energy, it has carbon chemistry, it has mineral surfaces, it has persistent environments, at least in some places, and enough time between many disturbances for chemical processes to unfold, but it does not yet have the protections, cycles, or atmospheric composition that later life depends on. There is no ozone layer shielding the surface, because oxygen has not yet accumulated enough to build one. Ultraviolet radiation reaches exposed environments more freely. The atmosphere lacks breathable oxygen and contains gases that would seem poisonous or suffocating to later animals. The land, where it exists, is barren of forests, grasses, soil, insects, and all visible life. Even the word land can mislead, because early continental pieces are probably small, scattered, and unstable compared with the continents of the present. The oceans are unlike modern seas. Their chemistry is shaped by dissolved iron, intense volcanic input, and a world with very little free oxygen. In many places the water may carry a dark, mineral heaviness, because the chemistry of the planet has not yet been transformed by biology. At this distance and time, it is tempting to imagine the Archean as empty. In visual terms, it mostly is. There are no reefs of coral, no fish, no kelp forests, no shells on beaches, no birds moving over waves. Yet emptiness is not the same as simplicity. A world without animals can still be active at every scale. The mantle convects slowly below. Magma rises where rock partially melts. Crust forms, cools, fractures, and sinks. Oceans circulate through heat and chemistry. Atmosphere and ocean exchange gases. Sunlight drives reactions near the surface. Impacts interrupt. Tides pull. Minerals act as surfaces where molecules can attach, concentrate, and change. The planet is not waiting passively for life. It is already a machine of gradients, and gradients are places where work can happen. Temperature changes with depth. Chemistry changes across vents and shorelines. Light fades with water. Pressure rises downward. Every boundary becomes a possible site of transformation. In this sense, the Archean opens with the planet learning to hold differences without immediately erasing them. A fully molten world destroys boundaries almost as soon as they appear. A more stable world preserves them long enough for processes to repeat. Repetition matters. It allows rock to weather, oceans to circulate, minerals to accumulate, and chemical pathways to be tested across immense spans of time. The Archean does not need to begin with life in order to be directed toward the possibility of life. Its first achievement is more basic. It makes Earth into a place where change can leave a trace. The boundary with the Hadean is therefore not a clean curtain falling between one world and another. It is a slow hardening, a gradual increase in the survival of surfaces, waters, and rocks. It is the difference between a planet whose past is almost entirely hidden and a planet that begins to remember. This memory is fragile. Most of it will still be lost. The earliest Archean rocks that remain are scattered pages from a book repeatedly burned, soaked, buried, and rewritten. Yet even those pages show a world assembling the deep conditions of habitability. By the end of this threshold movement, Earth has not become gentle. It has become possible. It has oceans under strange air, crust strong enough in places to survive, heat enough to drive restless geology, and a sky still marked by the debris of its own formation. The next part of the story begins inside that uneasy balance, where impacts continue to arrive and water becomes one of the defining facts of the planet's surface. The Archean does not open on a quiet sea. It begins beneath a sky that still receives pieces of the solar system's unfinished construction, and each arrival forces the young planet to answer again whether any surface can remain stable for long. The late heavy bombardment, as it is often called, is not preserved on Earth as a clean field of craters, because Earth does not keep scars the way the Moon does. Its crust moves, melts, sinks, and is altered by water. Its oldest surfaces are mostly gone. Yet the wider inner solar system still carries the memory of that interval, and Earth, lying in the same region of space, would not have been spared. Between roughly 4.1 and 3.8 billion years ago, asteroids and comets cross the planet's path more often than they will in later time, striking with enough energy to open the crust, vaporize rock, raise curtains of debris, and in the largest events send heat through ocean and atmosphere together. The young world is not simply cooling, it is being interrupted as it cools, and each interruption resets part of the surface, while leaving other regions to continue their slower changes. What makes this period difficult to understand is that impact is not a single kind of event. A small body entering the atmosphere may burn, fragment, and leave behind only chemical traces. A larger one may carve a basin, melt local crust, and throw material across a continent-sized region that does not yet resemble a continent in the modern sense. A truly immense collision can briefly change climate, ocean chemistry, and the physical state of the surface. The Archean Earth likely experiences the whole range. Some impacts are frequent and regional. Others are rare enough to become planetary disturbances. Together they give the Archean a rhythm of partial recovery and renewed damage, where a landscape may begin to weather, gather sediment, and interact with water, only to be broken again by falling stone. Yet even here, the story resists a simple picture of destruction. The material arriving from space is not all the same. Rocky asteroids bring metals, silicates, and compounds formed in the colder chemistry of the early solar system. Comets carry dust, carbon-rich molecules, and ices that can release water and other volatiles when they strike or break apart. Earth already has water by this time, from its formation, from minerals that held it, and from gases released by the interior. The old idea that oceans were supplied only by late comets is too simple, but impact delivery may still matter, not necessarily as the single origin of Earth's water, but as part of a continuing exchange between planet and solar system. Every icy body that reaches the surface adds something to the inventory. Every carbon-bearing fragment widens the chemical mixture. Every collision exposes fresh rock to liquid water, heat, and atmosphere. The same strike that sterilizes one region may prepare another with new minerals, new basins, and new reaction pathways. This is the strange double meaning of bombardment. It threatens habitability while also helping define the materials from which habitability is built. Water is the quiet center of that contradiction. In the Archean, water is not merely a surface feature. It is an active force working against the violence of heat and impact. When rain falls through a volcanic atmosphere, it carries dissolved gases into pools, streams, and seas. When ocean water enters fractures in hot crust, it returns altered, carrying metals and dissolved minerals upward. When an impact excavates rock, water invades the wound, cools the melt, circulates through broken layers, and changes the chemistry left behind. Even catastrophe becomes porous to water once the initial heat fades. A crater can become a basin. A field of shattered rock can become a network for fluid flow. A sheet of fresh volcanic material can become a surface for chemical alteration. The planet's ability to keep liquid water through this period matters more than almost any single impact, because liquid water gives the surface continuity. It allows reactions to repeat. It links distant environments through circulation. It turns isolated pieces of crust into part of a broader geochemical system. The oceans of this time are not modern blue expanses in any ordinary sense. They form beneath air with little free oxygen, with volcanic gases entering from below, and possibly with large amounts of dissolved iron that remain soluble in the absence of oxygen. Their chemistry is shaped by hot crust, submarine volcanism, and constant exchange with the interior. Near hydrothermal systems, water may be darkened and enriched by metals. In shallower settings, it may meet sunlight, sediment, and freshly weathered minerals. Around impact sites, the chemistry may become briefly extreme, heated and loaded with dissolved material from shattered rock. There is no single Archean ocean environment. There are many, changing with depth, temperature, location, and time since disturbance. This variety is important because early Earth's habitability does not require the whole planet to be gentle. It requires that some places remain suitable long enough, or return to suitability often enough, for chemistry to accumulate complexity. The bombardment makes that requirement harder, but not impossible. Large impacts can boil surface water locally or perhaps regionally, and the biggest events may send steam and dust into the atmosphere on a scale difficult to picture calmly. But oceans are massive heat reservoirs. Deep water can protect environments from surface extremes. Crustal fractures can shelter hot circulating fluids below the reach of ultraviolet light. Mineral surfaces can preserve chemical structure after open water has been disturbed. If life has not yet appeared, these refuges still matter as chemical settings. If very early life already exists somewhere, they become possible shelters through episodes that erase surface evidence. This is why the Archean record remains so frustrating. The absence of surviving fossils from the earliest interval does not prove absence of biology. It only shows how thoroughly the evidence could be destroyed. Impact, volcanism, metamorphism, and tectonic recycling all work against memory. The planet may have held delicate beginnings in places that left no readable trace. The Moon, meanwhile, moves gradually farther from Earth, and that slow retreat changes the background rhythm of the planet. In the earlier aftermath of its formation, the Moon would have raised stronger tides than it does today. By the Archean, those tides are weakening across immense time, but they still stir shallow seas, coastal margins, and perhaps the edges of early crustal islands. Tidal cycling may expose minerals to alternating wet and dry conditions where land exists, while submarine settings continue their own chemical exchange below. The exact landscapes are uncertain, but the processes are clear enough to matter. Earth is not a static target being struck from space. It is a wet, heated, rotating planet with tides, weather, volcanism, and an interior that refuses to become still. Bombardment acts upon that system, and the system answers by absorbing, altering, and redistributing the consequences. The end of the heaviest impact interval is not a sudden peace, it is a fading pressure. By around 3.8 billion years ago, the rate of large impacts appears to decline, though dangerous collisions continue throughout the Archean and far beyond. This decline allows longer stretches of surface continuity. Basins last longer. Sediments have more time to accumulate. Hydrothermal systems can mature. Crustal fragments can survive repeated alteration without always being completely reset. The planet begins to move from a condition dominated by interruption toward one in which endurance becomes more common. That shift is subtle but decisive. A world can have oceans and still fail to preserve the settings needed for complex chemistry if every environment is erased too quickly. A world can have energy and still be too violently renewed for delicate sequences to persist. The easing of bombardment does not make Earth calm, but it lengthens the pauses between the largest disturbances. Inside those pauses, water keeps working. It wears down fresh rock. It carries ions into the sea. It circulates through hot crust and returns with chemical energy. It fills basins and links them into larger systems. It gathers above a planet that has already survived melting, collision, and the birth of its moon. In the Archean, the ocean is therefore not simply a sign that Earth has cooled. It is the medium through which the planet begins to recover from each new wound without returning to the beginning. The craters fade, the melted rock crystallizes, the steam condenses, and the chemistry continues. What remains after bombardment is not a finished world, but a wetter and more persistent one, carrying within its battered crust the first long intervals in which ancient environments may finally leave a deeper record. The first stable crust of the Archean is not a continent in the comfortable modern sense. It is more like a set of stubborn fragments, buoyant patches of altered rock that manage to remain near the surface while much of the young planet is still being made, broken, buried, and remade. In the Archean, the surface is not empty, but it is hard to preserve. New basalt forms where mantle material rises and melts. That basalt cools into dark volcanic crust, then is fractured by heat, invaded by seawater, covered by younger flows, or dragged back toward the interior. Most of it does not survive as a witness. The rare pieces that do survive matter because they show that Earth has begun to develop a memory deeper than sediment alone. Somewhere within the violence of impact, volcanism, and ocean alteration, portions of crust become thick enough, chemically distinct enough, and buoyant enough to resist immediate recycling. They are not yet wide green continents or dry platforms under a familiar sky. They are the first long-lived foundations, and their survival changes the planet's future. The chemistry of these early foundations suggests a world still very different from later Earth. Modern continents are dominated by lighter, silica-rich rocks that stand high above ocean basins. The earliest Archean crust likely begins with much more basaltic material, but within that dark crust, repeated melting and alteration can create lighter components. When hydrated basalt is buried, heated, and partly melted, it can produce pale rocks known by a group of names that geologists abbreviate as tonalite, trondiamite, and granodiorite. These are not ordinary words in a sleeping landscape, yet they mark an important planetary transition. They describe rocks that are more buoyant than oceanic crust and more likely to endure. Their formation suggests that water has already entered the crustal engine. It also suggests that young Earth is sorting itself, separating darker, denser material from lighter material that can remain above the mantle's downward pull. The first stable crust therefore carries a quiet implication. Water, heat, and rock are no longer acting as isolated ingredients. They are beginning to build architecture. Ancient terrains preserved today in places such as southwest Greenland, northern Canada, and parts of Australia are remnants of that architecture, though each has been altered by the enormous pressure of later time. Rocks from the Isua region of Greenland, for example, do not offer a simple photograph of the Archean world. They have been heated, deformed, folded, and chemically changed. Yet they still preserve enough of their origin to show that sedimentary and volcanic environments existed by the early Archean. Some rocks appear to have formed from material laid down in water. Others record volcanic activity, submarine alteration, or early crustal growth. Their meaning does not come from perfection. It comes from survival. A rock that has endured nearly 4 billion years of planetary change is already an exception, and every mineral inside it has passed through a long history of stress. The scientist reading it is not reading a clean page. The record is more like a message pressed into stone, then crumpled, buried, heated, and only partly unfolded. Even older hints come from mineral grains rather than full rocks. Zircons, tiny crystals of zirconium silicate, can survive conditions that destroy the rocks around them. Some ancient zircons from Western Australia are older than the Archean itself, reaching back into the Hadean, but their importance continues into this story because they show that crustal material and liquid water may have existed very early. A zircon can trap isotopic information, a kind of chemical memory, inside a crystal only a fraction of a grain of sand. Some of these grains suggest interaction with water and the formation of relatively evolved crust before the Archean was fully underway. They do not reveal a coastline or a mountain range. They do not prove a stable continent stretching across the horizon. But they do weaken the image of early Earth as a uniform lava sphere for hundreds of millions of years. The planet may have cooled in uneven steps, creating habitable or at least water-bearing surfaces earlier than a simple molten world picture would imply. That distinction matters because stable crust is not merely scenery. It changes how the ocean, atmosphere, and interior communicate. Dark oceanic crust is dense and tends to be short-lived when a planet has active recycling. Lighter continental fragments can persist, weather, rise above surrounding basins, and supply minerals to water over long periods. They create shallow shelves and margins where waves, tides, sunlight, and sediment can interact. They allow rivers, if rainfall and relief are sufficient, to carry dissolved elements from exposed rock into the sea. They provide surfaces that are neither fully deep ocean nor fully volcanic vent, but intermediate environments where chemistry can be concentrated and repeated. The earliest fragments may be small, but smallness does not make them unimportant. A single durable crustal block can host a range of settings along its edge's submerged slopes, shallow basins, hot springs, volcanic plains, and mineral-rich shores, in a world still lacking plants, soils, and animals. The shape of rock itself defines most ecological possibility, even before ecology in the later sense exists. The making of stable crust also reveals a deeper uncertainty about early tectonics. Modern Earth is shaped by plate tectonics, with large plates moving across the surface, colliding, sinking, and spreading apart. In the Archean, the system may not yet work in the same way. The mantle is hotter. The crust may be weaker in some places and thicker in others. Instead of neat, modern-style subduction everywhere, early Earth may use a mixture of processes sinking blobs of dense crust, vertical dripping into the mantle, local burial and melting, plume-driven volcanism, crustal overturn, and perhaps the beginnings of plate-like motion in certain regions. The evidence does not force a single simple answer. It suggests transition, not instant modernity. Earth is learning, through physics rather than intention, how to move heat outward while building surface structures that can last. This makes the first stable crust a record of negotiation between two demands. The interior needs to lose heat. The surface needs to preserve some of what heat creates. Too much recycling and the record disappears. Too little internal motion and the planet's chemistry stagnates. The Archean seems to sit between these extremes, restless enough to renew itself, but increasingly capable of leaving behind survivors. The atmosphere and ocean respond to this crustal survival. Fresh volcanic rock reacts quickly with water and carbon dioxide, drawing some carbon into minerals while releasing other elements into the sea. Weathering, even without forests or soil animals, begins to link air, water, and stone. Rainfall over exposed crust dissolves material. Streams or sheet flow carry it downward. Waves grind rock into sediment. Chemical precipitates settle on sea floors. Over time, these processes begin to store pieces of the atmosphere inside the crust and store pieces of the crust inside sedimentary layers. This is one reason continental fragments matter so much. They increase the number of boundaries where exchange can occur. A planet covered only by deep ocean and short-lived basalt would still have chemistry, but a planet with emerging crustal rafts has more varied chemistry. Variation again becomes the hidden engine of possibility. There are warmer basins and cooler margins, fresh volcanic surfaces and altered ancient ones, deep hydrothermal systems and sunlit shallows. Each setting filters the same planetary ingredients in a different way. The landscape remains austere. No roots hold sediment. No moss softens stone. No animals disturb the shore. Exposed land, where it rises, is raw mineral surface under a dimmer sun and a dense, oxygen-poor atmosphere. Rain may fall on dark volcanic plains, feeding streams that carry iron and silica toward the sea. Tides may cover and uncover low margins of rock. Heat may rise through fractures, turning groundwater into hot chemical streams. There is no green yet, except perhaps in later microbial films once life spreads into visible mats. At this stage, the importance of land is not beauty but persistence. Land allows cycles of wetting and drying. It allows sunlight to strike mineral surfaces directly. It allows erosion to concentrate grains in basins and shorelines. It breaks the ocean's chemical uniformity. Even a small patch of stable crust can become a platform where time accumulates, because reactions that happen once can happen again, and reactions that happen again can begin to matter at geological scale. The first stable crust is therefore one of the Archean's quiet thresholds. It does not announce itself with a single event. It appears in the survival of minerals, in the chemistry of altered rocks, in the scattered remains of ancient terrains, and in the growing ability of Earth's surface to hold shape through repeated disturbance. From these fragments, later continents will eventually grow. From their margins, sediments will collect. From their erosion, oceans will receive a steady supply of elements. From their endurance, the planet will gain a longer and more readable record. Nothing about this process is complete by the early Archean. The crust is still too mobile, too hot, and too often reworked to resemble the stable continents of later time. But the direction has changed. Earth is no longer only forming crust that vanishes. It is beginning to keep some of it, and once the planet can keep its stones, it can also keep the traces of oceans, atmospheres, and eventually life along their edges. The Archean Ocean is not simply water spread across young rock. It is a planetary solvent under a sky that would make the later Earth feel almost unrecognizable. In the early and middle Archean, the air contains almost no free oxygen, and that one absence changes nearly everything. Iron can remain dissolved in seawater without immediately rusting out. Methane can persist more easily than it would under an oxygen-rich atmosphere. Volcanic gases can enter the air and sea without being processed by the kinds of biological and chemical cycles that later stabilize the planet. The sky above the ocean may be hazy, tinted by reactions between sunlight and methane, while the sun itself is fainter than it will be in later time. Yet the planet does not lie frozen beneath that weaker light. A thick blanket of greenhouse gases helps hold warmth close to the surface, and the ocean becomes the broad receiving body for heat, minerals, gases, and the slow consequences of a planet still releasing its interior. To stand outside time and look across it would not be to see a blue world in the modern sense. It would be to see water under strange air, moving around volcanic islands and dark crustal ridges, carrying a chemistry that belongs to a younger Earth. The colour of that water is uncertain, because colour depends on depth, minerals, light, particles, and atmosphere together, but it is unlikely to match the clean image of a modern tropical sea. In the absence of abundant oxygen, dissolved iron may give many waters a chemical richness that later oceans cannot hold in the same way. Silica, released from the alteration of volcanic rocks, may be more abundant too, because organisms that later use silica to build shells do not yet exist. Around vents and volcanic margins, metals and sulfur compounds enter the water in concentrated streams, in shallow regions. Waves and tides stir sediments made from fresh basalt and early continental material. Every part of the ocean is connected to rock that is still warm, reactive, and often newly formed. The sea is not a passive covering laid over the crust. It is part of the crust's transformation, entering cracks, dissolving minerals, depositing new ones, and carrying chemical messages from one environment to another. Beneath that atmosphere, weather begins to act without any of the living surfaces familiar from later time. There are no forests to slow rain, no roots to hold slopes, no soil communities to mix the ground, no shells to buffer shallow water, and no grasses to soften the edges of streams. Rainfall meets bare rock. Carbon dioxide dissolves into water and forms weak acids. Those acids attack exposed minerals, releasing ions that travel toward basins and seas, on volcanic islands and early crustal blocks. Erosion may be sharp and direct, with sediment produced by physical breakdown, heat stress, impact debris, and chemical alteration. The shorelines are raw boundaries between water and stone. They may shift quickly where land is low, where crust is unstable, or where volcanic construction and erosion compete. Yet these unsettled margins are important precisely because they are boundaries. At a shoreline, atmosphere, sunlight, water, and minerals meet in a repeated pattern. Wet surfaces dry and are wetted again. Sediments concentrate. Salts form and dissolve. Minerals are exposed to changing conditions. The ocean's edge becomes a place where chemistry does not simply disperse into depth, but gathers, cycles, and sometimes lingers. The deep ocean offers a different kind of persistence. Away from sunlight and weather, water enters the fractured seafloor, sinks into hot crust, heats, reacts, and rises again through hydrothermal systems. These systems may be widespread because young crust is warm and volcanic activity is common. They release dissolved metals, reduce compounds, and heat into the sea, creating steep chemical gradients. A gradient is difference that can do work hot against cold, acidic against alkaline, reduced against oxidized, concentrated against dilute. In the Archean, such differences are among the most important features of the environment. They create places where matter is pushed out of equilibrium, and life, when it exists, depends on that kind of imbalance, even before biology becomes clearly visible in the rock record. The ocean floor may contain settings where chemistry is driven again and again by the movement of water through rock. Some of these settings may be too hot or too unstable. Others may be sheltered and long-lived. The difficulty is not finding energy on the young Earth. The difficulty is understanding which forms of energy could be captured, organized, and repeated in ways that matter for the origin and early spread of life. The atmosphere above this ocean deepens the problem. Without abundant oxygen, there is no protective ozone layer of the sort that later reduces ultraviolet radiation at the surface. Ultraviolet light can be destructive to fragile molecules, breaking chemical bonds and interfering with complex pathways, but it can also drive reactions that would otherwise proceed slowly. This creates another Archean contradiction. The same sunlight that threatens delicate chemistry may help produce reactive compounds. The same absence of oxygen that leaves the surface exposed also allows methane, iron, and other reduced materials to persist. The planet is not arranged for life in any simple or gentle way. Instead, it provides a set of overlapping conditions, some favourable, some hostile, some useful only in the right place and in the right sequence. A shallow pool exposed to ultraviolet light may generate certain molecules, then dry, concentrate them, and later reconnect with a wider body of water. A deep vent may shelter chemistry from radiation, but expose it to heat and mineral surfaces. A shoreline may mix atmospheric products with dissolved minerals from the sea. These are not scenes of certainty. They are possible arenas, each with its own limits. Climate in this ocean world is held in a delicate argument between a fainter sun and a stronger greenhouse atmosphere. Methane may play a particularly important role, especially if produced by geological processes or later by microbes. Carbon dioxide supplies another layer of warming, though too much can acidify rain and oceans while too little risks cooling. Nitrogen may form much of the background air, but it does not by itself warm the planet strongly. The balance among these gases is not fixed. Volcanism adds carbon dioxide and sulfur gases. Weathering removes some carbon dioxide into minerals. Impacts can briefly alter the atmosphere. Early biological activity, once established, begins to push chemistry in new directions. The climate is therefore not just weather averaged over time. It is negotiation among the interior, the surface, the ocean, the atmosphere, and eventually life. During the Archean, that negotiation keeps liquid water present across enormous spans of time. Despite conditions that might seem unstable from a modern perspective, the ocean becomes the evidence of that success. If it had frozen completely and remained frozen, the story would narrow. If it had boiled away, the story would end. Instead, it stays, altered again and again, but present enough to shape the planet. The seafloor beneath those waters is likely the dominant landscape of Earth. Dry land exists, but it is limited compared with later continents. Much of the planet's surface is ocean over volcanic crust, crossed by ridges, plateaus, basins, and regions of intense alteration. In such a world, the deep sea is not remote in the way it feels now. It is central. Heat loss, chemical exchange, mineral deposition, and perhaps early metabolism all point downward into the dark. At the same time, shallow settings remain crucial because they connect the ocean to sunlight and atmosphere. The Archean Ocean cannot be understood as one environment. It is a layered system, with bright surfaces, restless margins, hot depths, mineral walls, suspended particles, and chemical gradients spread across a planet still finding its long-term rhythm. This layered complexity allows different processes to coexist without needing the whole world to be favourable at once. Some environments may destroy complexity, others may preserve it, some dilute chemistry, others concentrate it, some are renewed too quickly, others endure. What emerges from this picture is a world without visible life in the familiar sense, yet full of preparation. The ocean holds dissolved elements from fresh crust. The sky supplies gases and photochemical products. Volcanoes supply heat and new material. Impacts disrupt and enrich. Tides move water across raw margins. Rain carries atmospheric chemistry into basins. None of these features guarantees life, and none should be turned into an easy origin story. Their importance lies in combination. The Archean Sea is a place where the boundaries between geology, chemistry, climate, and biology begin to blur before biology has clearly taken command. It is not yet the ocean of fish, reefs, plankton blooms, or oxygenated depths. It is an older ocean, heavier in its chemistry, darker in its possibilities, and more directly tied to the planet's interior. Under its strange sky, Earth becomes a world where water does more than collect. It reacts, shelters, dissolves, transports, and remembers. The next movement begins where that remembering becomes more intimate, in settings where heat, minerals, and flowing water may have helped simple chemistry approach the edge of inheritance. Hydrothermal systems are not dramatic because they are loud. Their importance comes from the way they bring hidden parts of the planet into contact with the ocean. One fracture, one mineral wall, and one stream of heated water at a time. In the Archean, when the crust is warmer and the seafloor is more directly tied to volcanic construction, these systems may be common features of the submerged world. Seawater slips into cracks in newly formed basalt, descends through rock still carrying internal heat, reacts with minerals under pressure, and returns changed. It may emerge hotter, richer in dissolved metals, altered in acidity, and carrying chemical energy from the interior into the open sea. Around each vent, the water does not simply mix and vanish, it creates gradients, and gradients are the quiet engines of early Earth. Hot water meets cold, mineral-rich fluid meets ordinary seawater, reduced compounds, which can give up electrons, meet more oxidized surroundings, which can receive them. In that difference lies the possibility of work. The young ocean is full of such boundaries, but hydrothermal settings concentrate them in one place. They make steep contrasts durable enough to matter. That durability is why they remain central in many discussions of life's earliest chemistry. A molecule floating alone in a vast ocean is easily diluted, broken, or lost. A molecule held against a mineral surface, trapped in a pore, or repeatedly supplied by flowing water has a different kind of future. The vent environment can provide tiny compartments in rock, natural channels where fluids pass through, and reactions are refreshed. Some minerals can attract and hold molecules long enough for new bonds to form. Iron and sulfur minerals, common in certain hydrothermal systems, can participate in electron transfer, helping reactions move in directions that would otherwise be difficult. Alkaline vents, where high pH fluids meet a more acidic ocean, may create natural proton gradients, differences in charged particles across thin mineral barriers. Modern cells use controlled gradients across membranes to store and release energy. That does not mean ancient vents contained living cells waiting to appear fully formed. It means that geology may have provided a rough physical echo of one of biology's deepest habits, using separation to make energy manageable. The distinction is important because origin of life chemistry cannot be explained by a single lucky ingredient. It requires organization. Carbon compounds must form, persist, concentrate, react, and in some pathways begin to copy or influence their own production. Each step has its own difficulty. In open water, useful molecules may become too dilute. In extreme heat, they may break apart. In dry settings, they may concentrate but then lack stable fluid circulation. In shallow sunlight, some reactions may be helped while others are destroyed. Hydrothermal environments solve some problems while creating others. They supply energy and mineral surfaces, but many are too hot for delicate molecules. They offer compartments, but not all compartments are stable. They provide continuous flow, but continuous flow can also carry products away. This is why the question remains scientific rather than settled. The deep chemical settings of the Archean are not a finished answer. They are a set of plausible stages where part of the answer may have unfolded. Along volcanic shorelines, a different chemistry becomes possible. There, rock, air, rain, sunlight, and seawater meet more directly. Pools may form in hollows of basalt or on the edges of early continental fragments. Waves bring dissolved compounds. Evaporation concentrates salts and organics. Rain dilutes them again. Wet surfaces dry, then are flooded, then dry once more. This cycling can drive reactions that do not happen as readily in stable deep water. Some molecules join more easily when water is removed for a time, because water itself can oppose the formation of certain bonds. Later flooding can move the products elsewhere, mixing them with minerals and new reactants. Such settings are fragile and exposed. Ultraviolet light can damage complex molecules. Impacts or eruptions can destroy local basins. But their vulnerability does not erase their value. A shoreline is not useful because it is safe. It is useful because it changes repeatedly in patterned ways. Early chemistry may have needed exactly that kind of changing boundary, where concentration, exposure, dilution, and renewal follow one another without requiring a living system to control them. Mineral surfaces are another quiet force in this story. Clays, metal sulfides, silica-rich deposits, and altered volcanic glass can all influence chemical reactions by holding molecules, arranging them, or shielding them from immediate dispersal. A mineral is not alive, but it can impose order. It has charged surfaces, small spaces, repeating structures, and chemical preferences. In the Archean, when fresh rock is constantly being made and altered, mineral diversity near vents and volcanic margins may be high. Water passing through hot crust can deposit chimneys, crusts, and layered precipitates. Weathering of land and shallow seafloor can create fine particles that drift into basins. Impact sites can produce glassy and fractured materials with abundant reactive surfaces. Each surface offers a different possibility. Some may destroy fragile compounds, others may gather them, others may act as templates, not in the genetic sense, but in the simpler sense of helping molecules line up in ways that make reaction more likely. The early planet does not need to choose only one setting. Its strength is multiplicity. Chemistry could proceed in vents, pools, sediments, ice at rare cold margins, volcanic ash beds, and porous rocks, with products moving between them over time. The idea of movement between settings matters because no single environment may provide everything. A molecule formed by atmospheric chemistry may fall with rain onto rock. It may wash into a pool, concentrate during drying, join with other compounds, then be carried into the ocean. It may bind to a mineral grain, sink into sediment, enter a hydrothermal circulation system, and emerge altered. Much of this chemistry would lead nowhere. Most pathways would fail, scatter, or reset. But over millions of years, repeated movement allows the planet to test combinations at a scale no laboratory can truly reproduce. The Archean is not conducting an experiment in the human sense. It is a world of countless uncontrolled trials, each shaped by temperature, pressure, acidity, mineral type, radiation, concentration, and time. The phrase origin of life can make the event sound singular, as though there were one place and one moment where non-living matter crossed a bright line. The reality may be less sharp. Early life may have emerged through networks of chemical systems that became increasingly self-sustaining before any clear boundary could be drawn. Some systems may have carried energy in primitive cycles. Some may have stored information imperfectly. Some may have formed membranes or membrane-like compartments. Some may have failed after long persistence. In this older view, the beginning of life is not a spark in darkness but a long narrowing, in which chemistry gradually gains continuity, then inheritance, then evolution. What makes the Archean so powerful is that it contains the settings where such narrowing could happen. Even if the decisive evidence has been almost entirely erased, the rocks of this age have suffered heat, deformation, and recycling. Organic traces can be altered beyond recognition. Isotopic signals can be suggestive but disputed. Structures that look biological may also have non-biological explanations. The planet's earliest chemistry is therefore approached through constraints rather than direct observation. The conditions must fit what is known of early Earth. They must explain how simple molecules formed in sufficient amounts. They must show how energy was captured, how concentration occurred, how compartments developed, and how information-bearing chemistry became possible. No proposed pathway escapes difficulty. Deep vents provide energy but may challenge stability. Shallow pools provide concentration but may challenge survival. Mineral surfaces provide order but not necessarily inheritance. Atmospheric synthesis provides ingredients but not organization. The importance of the Archean is that these difficulties do not stand alone. They overlap. A weak point in one setting may be answered by transport to another. A molecule damaged in one environment may be protected in sediment. A reaction impossible in open water may proceed on a mineral wall. A compound formed under sunlight may become useful only after entering darkness. The planet's unevenness becomes part of the explanation. In the calmest sense, early Earth is not a cradle so much as a network of thresholds. At each threshold, matter crosses from one condition into another and is tested by the crossing. Water through rock, gas into rain, sunlight into surface chemistry, heat into mineral structure, dissolved carbon into more complex compounds, compartments into persistence, persistence into memory. The next question is whether any of those crossings left traces that can still be recognized. When the first evidence of life finally appears in the Archean record, it does not arrive as a creature or a body or a sudden announcement. It appears as subtle structure, chemistry, and pattern, the kind of evidence expected from a biosphere that began not with visibility, but with cells too small and fragile to leave easy fossils. The first signs of life in the Archean do not appear as bones, shells, leaves, tracks, or anything that resembles the later fossil record. They appear at the edge of certainty, in chemical ratios, layered rocks, microscopic textures, and structures whose meaning must be tested against the possibility that geology alone could have made them. This is why the earliest life evidence feels both powerful and fragile. By the Paleo-Archean, around 3.5 billion years ago, Earth's surface has already held oceans for a very long time, and the planet has developed enough stable crust for some environments to leave a record in those surviving rocks, especially in ancient terrains such as the Pilbara region of Western Australia and the Barberton Greenstone Belt of southern Africa. There are traces that suggest microbial communities had become part of the surface world. These traces do not show complex organisms. They do not show animals, plants, fungi, or any visible architecture of the kind that later fills the planet. They suggest cells, colonies, mats, and metabolism, life acting at a scale so small that the rocks preserve its consequences more readily than its bodies. The difficulty begins with age and alteration. Such a rock may have been buried, heated, squeezed, folded, invaded by fluids, and chemically changed. Minerals can grow after the original sediment was laid down. Carbon can move. Textures can be changed. A structure that seems biological can sometimes be made by physical layering, chemical precipitation, or deformation. This does not make the evidence meaningless. It means the evidence has to be handled with unusual care. In the Archean, biology and geology meet so closely that the border between them can blur. A microbial mat can trap sediment and build a layered form, but so can certain mineral processes. Living cells can prefer lighter carbon isotopes, leaving a chemical signature, but later alteration can complicate the signal. The question is rarely whether one clue alone proves life. The stronger case comes when structure, chemistry, setting, and repetition point in the same direction. Among the most important signs are stromatolites, layered structures formed when microbial communities trap, bind, or influence sediment over time. In later and modern settings, stromatolites can be built by living microbial mats, including communities with cyanobacteria. In Archean rocks, some ancient layered forms resemble these biological structures, especially when they occur in shallow water settings where mats could have interacted with sediment and sunlight. Their significance is not only their shape, it is the behavior implied by their growth. Layer upon layer suggests a surface community that persisted, trapped particles, responded to light or water movement, and kept building upward as sediment accumulated. A single dome or wrinkle might be ambiguous. A repeated field of layered, organized forms in a plausible environment becomes harder to dismiss. Still, caution remains. The earliest stromatolite-like structures are debated because non-living chemistry can produce surprising patterns. The ancient rock record asks for patience rather than quick certainty. Life, if it is recorded there, has left a whisper, not a declaration. Chemical evidence can be just as subtle. Living systems use carbon, and many metabolic processes slightly favour lighter carbon over heavier carbon. When ancient rocks preserve carbon with such a pattern, it may suggest biological activity. In some Archean rocks, carbon isotope signatures have been interpreted as possible evidence for early metabolism. The strength of that interpretation depends on context. The carbon must be ancient, not introduced later. The surrounding rock must preserve enough of its original setting to make the signal meaningful. Alternative non-biological processes must be considered. This is why early life evidence often advances through convergence rather than spectacle. A layered shallow water structure, associated carbon, sedimentary context, and comparison with younger biological examples may together suggest a biosphere already active on the young Earth. None of this requires life to have begun exactly where the evidence is found. It only shows that by the time those rocks formed, life may have already been established enough to leave environmental traces. That distinction opens the deeper possibility that life originated earlier, perhaps in the Archean, or even before the preserved record becomes readable. If microbial ecosystems are already visible or nearly visible by the Paleo-Archean, then the transition from chemistry to biology may have taken place during an even more obscure interval. The oldest surviving evidence may not mark the beginning of life at all. It may mark the earliest place where Earth still remembers life. That possibility changes the emotional shape of the Archean. The most important beginning may be hidden behind the loss of older rocks, concealed by metamorphism, recycling, and impact destruction. The record does not show a clear first cell. It shows that by a certain point, the planet's chemistry had crossed into something capable of growth, reproduction, and evolution. A microbial cell is a highly ordered system. It holds a boundary between inside and outside. It manages energy. It carries information. It builds molecules that help build more of itself. Even the smallest early cells would represent a profound shift from chemistry that merely happens to chemistry that preserves successful patterns across generations. Once inheritance exists, Earth changes in a new way. Before life, environments can alter molecules. After life, molecules can respond to environments through selection. Variation can be tested. Useful traits can become more common. Metabolic pathways can become refined. Communities can spread into settings that suit them and disappear from those that do not. The planet gains not only chemistry, but memory with a biological direction. Early Archean life was almost certainly microbial, and much of it may have lived without oxygen. In an atmosphere and ocean where free oxygen is scarce, the first metabolisms would have depended on other chemical pathways. Some organisms may have used hydrogen, sulfur compounds, iron, carbon dioxide, or simple organic molecules in ways that do not require oxygen at all. Such metabolisms still exist today among microbes in sediments, hot springs, vents, and other low oxygen settings. Modern examples are not fossils of the first life, but they show that life can thrive under conditions very different from the surface world familiar to animals. The Archean biosphere, if viewed from a later human perspective, would seem nearly invisible. It would not announce itself with forests or reefs. It would exist as films on sediment, colonies in shallow water, communities near chemical gradients, and perhaps cells suspended in the ocean. Yet from the planet's point of view, this invisible biosphere is a new geological force. Microbes alter their surroundings. They consume dissolved compounds. They release waste. They change mineral precipitation. They help trap sediment. Over time, those small differences accumulate. A mat only millimeters thick can influence how sediment settles. A community spread across a shoreline can change local chemistry. A metabolism repeated across millions of years can affect the ocean's inventory of elements. Early life is not powerful because any single cell is large. It is powerful because cells multiply, persist, and repeat. Repetition turns small chemistry into planetary consequence. The earliest evidence of life therefore marks more than the appearance of organisms. It marks the beginning of feedback between the biosphere and Earth's surface. geology creates environments, and life begins to modify them. Rock supplies minerals, and microbes influence which minerals form. Water carries nutrients, and cells change the chemistry of the water that surrounds them. Sunlight, heat, and chemical gradients remain the primary sources of energy, but biology begins to route that energy through living structures. The atmosphere does not suddenly fill with oxygen. The continents do not turn green in the plant-like sense. The oceans do not become crowded with visible bodies. The shift is quieter and more durable. Life becomes part of Earth's operating system while almost no obvious sign of it exists from a distance. This makes the Paleo-Archean one of the most understated revolutions in planetary history. The planet may look barren, volcanic, and oceanic, yet along certain margins and basins, matter has learned to reproduce. The implications extend beyond Earth's own past. If life can arise early on a planet that has only recently emerged from bombardment, high heat, unstable crust, and an alien atmosphere, then habitability may not require a world to become gentle before biology begins. It may require only persistent niches, liquid water, energy, carbon chemistry, and time enough for complexity to take hold somewhere. But that inference must remain careful. Earth is the only known example. Its early life evidence is ancient, altered, and incomplete. The Archean does not prove that life is easy. It proves that on this planet, under these conditions, life became possible early enough to be woven into the rest of the story. From this point onward, Earth can no longer be described only through oceans, crust, atmosphere, and impact. It has another layer, thin at first but irreversible in its consequences. The next stage carries that layer to the edges of early land, where ancient crustal fragments and shallow waters create margins on which microbial communities can spread, build, and begin to leave the planet's first living architecture. Valbara is less a continent in the modern imagination than a name given to a difficult pattern. It gathers together some of the oldest surviving pieces of crust, especially in regions now separated as Western Australia and Southern Africa, and treats them as possible fragments of a larger early landmass. The idea does not rest on a preserved outline, because no complete Archean map remains. It rests on matching ages, rock types, magnetic clues, and geological histories that suggest distant terrains may once have belonged together. In the Paleo-Archean, such a landmass would not have resembled a modern continent with forests, rivers full of animals, soils, and broad inland plains. It would have been raw mineral ground, dark volcanic surfaces, lighter crustal bodies, shallow basins, steaming fractures, and shorelines repeatedly altered by waves, tides, weathering, and burial. Yet even in that austere form, Valbara matters because it gives early life a geography. It suggests that the biosphere was not only a deep chemical possibility hidden in vents or a faint signal in scattered rocks, but something that could occupy the margins where ancient land met shallow sea. Along those margins, the planet offers a different kind of stability from the deep ocean. The water is shallower, light reaches the bottom, sediment can settle in thin layers. Waves and tides move grains across microbial surfaces. Volcanic ash falls into basins and becomes part of the record. Hot springs and hydrothermal fluids may enter nearby waters, adding dissolved elements to environments already exposed to sunlight and atmospheric chemistry. This mixture does not make the coast gentle, but it makes it varied. A mat of microbes on a shallow seafloor could be buried by sediment, then grow upward again. A pool could concentrate dissolved compounds during evaporation. A tidal flat could expose living films to drying, then cover them again. A shoreline could migrate as the crust rose, sank, fractured, or was drowned by changing sea level. Such settings are unstable in the short term, yet they can preserve repeated patterns over long time. The important feature is not calmness, it is recurrence. The same kinds of surfaces return again and again: wet mineral flats, sunlit sediment, shallow water, fresh volcanic material, and chemical gradients where land, ocean, and air overlap. The Pilbara region of Western Australia and the Barberton region of Southern Africa preserve some of the strongest windows into these ancient environments. They are not windows without distortion. Later deformation, metamorphism, erosion, and burial have changed them deeply. But they still contain layered volcanic and sedimentary sequences that point towards shallow marine settings, hot spring systems, and early crustal surfaces. In such rocks, stromatolite-like structures and other microbial signatures become more than isolated curiosities. They are placed inside landscapes. A dome of layered sediment has one meaning if it is seen alone, and a stronger meaning if it belongs to a wider setting of shallow water, repeated sedimentation, and microbial influence. Vaalbara's possible margins therefore help turn early life from a chemical abstraction into a surface presence. The organisms themselves remain microscopic, but their environments can be imagined with more precision not as empty coastlines waiting for plants, but as living films spread across sediment, responding to light, water movement, and the chemistry of a planet with almost no oxygen in its air. The absence of oxygen shapes every part of these margins. Iron remains mobile in ways that would later become difficult. Organic matter is not decomposed through oxygen-breathing pathways in the familiar manner. Minerals form under conditions that belong to a reduced world, where many compounds have not yet been forced into the oxidized state common on later Earth. Microbes living there would not be guests in a modern-style ecosystem. They would be the ecosystem. A microbial mat can include many kinds of organisms layered together, each positioned according to light, chemistry, and access to nutrients. Cells near the surface may use sunlight if photosynthetic pathways are present. Others below may live on products made above, on sulfur compounds, on hydrogen, on iron, or on organic material trapped in the mat. Even in a thin film, there can be structure. The top can differ from the bottom. Day can differ from night. A buried layer can become part of the sediment while a new layer forms above it. This is how life begins to write into geology without leaving bodies large enough to see. It changes the way grains are trapped. It affects how minerals precipitate. It creates textures that, when lucky enough to survive, carry the memory of behavior rather than anatomy. The land behind these margins is almost as strange as the life along them. Without plants, weathering works directly on rock. Rain falls on bare volcanic surfaces and early continental crust. There are no roots to pry minerals apart, no leaf litter to produce modern soil, no animals to churn sediment, no lichens in the later sense to cloak stone. The surface may be dark, uneven, and chemically fresh, with loose material moved by water, gravity, and wind. Streams may exist where rainfall and relief allow, though their banks are not held by vegetation. Sediment is likely carried quickly, spread into fans, washed into shallow basins, and reworked by waves. This makes the coast a place of constant exchange. Material from land enters the sea. Seawater invades cracks and low plains. Volcanic eruptions reset parts of the surface. Microbial communities colonize stable patches, are buried, disturbed, and recolonize again. The rhythm is not a simple march of expansion. It is a repeated negotiation between fragile living surfaces and a planet still too active to leave them undisturbed for long. Yet disturbance may help the biosphere as well as harm it. Fresh volcanic ash supplies reactive minerals. Newly exposed rock releases nutrients as it weathers. Shallow basins form and vanish, creating opportunities for colonization. burial can protect organic matter and microbial textures from later destruction, at least for a time. A mat destroyed at the surface may leave a layer below that becomes part of the rock record. In this way, early coastlines become both habitats and archives. They allow life to spread, and they give some of its activity a chance to be preserved. The preservation is uneven, rare, and often contested, but it is still a profound change from a world where chemistry leaves no biological pattern at all. On Valbara's margins, life begins to have a geography that can be followed through stone, even when the map is broken. The possible connection between Western Australia and Southern Africa adds another quiet implication. If these terrains were once joined, then early microbial environments may have extended across a larger region than any single outcrop now reveals. What appears today as separated evidence on opposite sides of the Indian Ocean may represent pieces of one ancient system, later split apart and carried by plate motion across deep time. This does not mean the entire landmass was covered in life. It means that suitable margins, basins, and shallow marine settings may have repeated across a broad crustal province. Life, once established, does not need a single birthplace to remain confined. It can spread wherever water, nutrients, energy, and tolerable conditions appear. In the Paleo-Archean, those conditions may have formed along many edges of early crust. Some communities would vanish without record. Others would be buried in ways that later heating would erase. A few would leave structures or chemical traces strong enough to survive into the present, not as full testimony, but as fragments of a vanished microbial world. The image of Valbara also changes the sense of scale in the Archean story. The previous movements have dealt with planetary conditions, bombardment, oceans, atmosphere, crust, and the first evidence of life. Here, the scale narrows to coastlines, basins, and mats. That narrowing is not a reduction in importance. It is where global processes become local habitability. A greenhouse atmosphere matters because it keeps shallow water liquid. Stable crust matters because it holds a basin in place. Weathering matters because it supplies nutrients. Tides matter because they move sediment over living surfaces. Volcanism matters because it provides heat, minerals, and new ground. The early biosphere exists in the meeting place of all these processes. It is not separate from geology. It is a thin living expression of geology's possibilities. This is why Valbara's ancient margins remain so important even when the supercontinent itself is partly reconstructed and uncertain. They represent a type of environment that the Archean increasingly provides shallow, mineral-rich, sunlit, and persistent enough for microbial communities to become builders. Once life can build, even in the simplest layered way, the planet's surface record changes. Sediment is no longer shaped only by current, gravity, and chemistry. It is also shaped by living films that hold grains, create surfaces, and rise through burial. The next section follows those structures more closely, because in stromatolites the Archean biosphere becomes visible not through bodies, but through layers of stone made meaningful by life. A stromatolite begins as something too thin to command attention. It may start as a film of microbes spread across sediment and shallow water, a living surface only a few cells thick, holding to grains that would otherwise shift with the current. Yet over time, that film can change the ground beneath it. Cells produce sticky substances. Fine particles settle and become trapped. Minerals precipitate within and around the mat. A new surface forms above the old one. And the community grows upward again. Layer follows layer, not as a deliberate structure, but as the repeated consequence of life meeting sediment under light, water, and time. In the Archean, this quiet building becomes one of the clearest ways that biology enters the visible record. The organisms themselves are mostly too small and soft to fossilize as bodies. Their architecture survives more easily than their anatomy. A stromatolite is therefore not a fossil in the familiar sense of a preserved creature. It is a record of behavior, a stone memory of microbial persistence. The importance of that distinction is hard to overstate. In later life, animals leave bones, shells, burrows, footprints, teeth, pollen, wood, and countless recognizable structures. In the Archean, life leaves evidence by modifying the way sediment accumulates. The form is indirect, but it is not weak. A layered dome or column can reveal a community that held its place through burial, light changes, mineral growth, and water movement. Each layer may represent a period when microbes colonized a surface, trapped grains, influenced chemistry, and then were partly covered before growing again. This is growth through interruption. It fits the Archean world well, because early environments are rarely calm for long. Storms, tides, volcanic ash, shifting shorelines, and chemical precipitation can all disturb a mat. But if conditions return, the living surface can re-establish itself. The rock that forms from this process carries a rhythm: surface, burial, recovery, surface again. That rhythm makes stromatolites valuable not only as signs of life, but as signs of life able to persist in a changing environment. The shallow seas where many stromatolites form are important because they combine ingredients that deep water cannot arrange in the same way. Sunlight reaches the sea floor. Sediment moves but does not always sweep everything away. Carbon dioxide and dissolved minerals are present. In some settings, volcanic or hydrothermal influence adds nutrients and chemical complexity. The water may be warm, iron-rich, and poor in oxygen, unlike most familiar coasts. The sky above lacks the protective oxygen-derived layer that later filters ultraviolet radiation, so exposed surfaces face a harsher light. Yet microbial mats can create their own small protected worlds. Upper layers may take the strongest radiation and light. Lower layers may live in dimmer. Chemically different conditions, dead cells, trapped sediment, and mineral crusts can shield what lies beneath. The mat is not just a flat skin, it is a vertical environment in miniature, with zones separated by fractions of a millimeter, each shaped by light, chemistry, and the activities of neighbouring organisms. This layered living structure may include many metabolic strategies. Some microbes use sunlight, others consume the products of those above them. Some rely on sulfur, iron, hydrogen, or organic compounds. In later microbial mats, such layered communities can be remarkably complex, even without large bodies or organs. Archean mats may not have been identical to modern examples, and the exact metabolisms present in the earlier stromatolite builders remain uncertain. But the principle is strong. Microbial life does not need size to become organized. It can divide space chemically. It can build gradients inside a mat just as the planet builds gradients between ocean and crust. At the scale of cells, sunlight, waste, minerals, and dissolved gases become a structured environment. This makes stromatolites more than sedimentary shapes. They are places where the biosphere begins to engineer small compartments on the planetary surface. Their growth depends on the outside world, but their internal conditions are partly produced by life itself. The oldest convincing stromatolite-like records are debated because deep time has damaged the evidence, and because non-living processes can imitate certain forms. This caution is not a weakness in the story, it is part of the story. A dome of layered carbonate or silica-rich sediment must be read with its environment, its microscopic texture, its chemistry, and its relation to surrounding beds. A purely physical current can create ripples and layers. Chemical precipitation can build crusts and domes. Deformation can reshape earlier deposits into misleading patterns. For a stromatolite interpretation to become persuasive, the structure must fit a biological process better than these alternatives. It should show growth forms consistent with microbial trapping or mineral mediation. It should sit in a plausible shallow water setting. It should recur in ways that suggest living surfaces responding to burial and exposure. The most careful readings do not ask the shape to carry the entire burden alone. They ask whether many lines of evidence lean in the same direction. In Archean rocks, that is often the best that can be done. The evidence does not become modern and clear simply because the question is important. It remains ancient, altered, and partial. Modern stromatolites, such as those known from hypersaline bays and other restricted environments, help explain the process, but they do not turn the past into a simple copy of the present. Today, stromatolites survive best in places where grazing animals and other competitors are limited. In the Archean, there are no animals to crop the mats or stir them apart. That absence may allow microbial surfaces to spread more freely across suitable shallow settings. A coastline without snails, worms, fish, or burrowing creatures is not empty if microbial mats cover the sediment. It is simply organized at a different scale. The surface may appear as dark, greenish, brown, or mineral-stained films over mud and sand, depending on chemistry and community composition. Gases may gather in small bubbles. Sediment may wrinkle and crack as mats dry or are buried. Waves may peel fragments away and redeposit them. In a world without plants, such mats could be among the few living textures visible across the margins of land and sea. They would not look impressive by later standards, but they mark a deep shift. Life has become a surface phenomenon. It is no longer only inferred in hidden pores or chemical gradients. It is spreading over environments and changing how those environments turn into rock. The act of trapping sediment may seem modest, but over geological time it gives biology a new kind of reach. A microbial mat can influence erosion by stabilizing grains. It can alter mineral precipitation by changing local acidity, alkalinity, and chemical concentrations. It can help form laminated deposits that preserve evidence of repeated growth. It can bury organic matter, creating small reservoirs of carbon that later heat and pressure may transform. These effects are local at first, but the Archean is long. A process repeated across shorelines for millions of years becomes a planetary factor, especially when no larger organisms exist to dominate the surface. Stromatolites show life beginning to participate in sedimentary geology. The seafloor is no longer shaped only by water flow, volcanic ash, mineral saturation, and gravity. It is also shaped by microbial communities that hold, bind, precipitate, and rise. This is one of the earliest forms of ecosystem engineering. Although the engineers are cells without awareness, following chemical possibilities one generation at a time, their structures also introduce a new kind of time into the rock record. A lava flow can freeze quickly. An impact layer can be laid down in a brief catastrophe. A stromatolite builds through repeated growth. Its layers imply continuity. They speak of an environment that remained habitable long enough for colonization to continue, or return to habitability often enough for the community to rebuild. This matters in the Archean because it shows that life was not merely a rare event surviving in isolated refuges. In at least some places, it could occupy stable enough surfaces to leave a pattern through time. The structure itself becomes a measure of persistence. Not every layer is a day, a season, or any simple unit. The timing can vary widely, but the presence of many layers means that the environment was not erased after one moment of growth. It endured, or it recovered. That endurance is one of the main themes of the Archean planet as a whole. Crust begins to endure, oceans endure, microbial communities endure. The world is still harsh, but it is no longer only transient. Stromatolite worlds are therefore both small and immense. They are small because their builders are microscopic, and their growth happens through thin films and fine grains. They are immense because they reveal a biosphere learning to occupy the planet's margins in a repeatable way. The same sunlight falling on a shallow seafloor can feed growth. The same sediment settling from the water can be trapped. The same mineral chemistry can be altered by cells. The same burial that threatens a mat can preserve its trace. In these layered stones, early life becomes visible as pattern rather than body, as texture rather than organism. The next change will widen that pattern further, because some of the microbes living in such worlds begin using sunlight in a way that does more than sustain themselves. They release a waste product that the planet has not yet learned to absorb forever, and over time that waste product will begin to unsettle the atmosphere, the oceans, and the climate of Earth itself. Photosynthesis begins as a solution to a local problem before it becomes a planetary force. A microbial cell living near the surface needs energy, and sunlight is the most constant energy source available across shallow water, tidal flats, and illuminated sediment. Long before forests, grasses, leaves, or even true algae, microbes learn to use light in chemical ways. Some early forms of photosynthesis do not release oxygen at all. They draw electrons from compounds such as hydrogen sulfide, dissolved iron, or other reduced materials, using sunlight to build organic matter without splitting water. These pathways matter because they show that light-driven life is not a single invention with a single consequence. It develops in stages, through metabolisms that fit a low-oxygen world. Yet at some point in the Archean, a more difficult and more consequential form appears: oxygenic photosynthesis, the kind that takes electrons from water and releases oxygen as waste. The cells that master this pathway, associated with cyanobacteria and their relatives, are not large, dramatic, or visible as individuals. Their power lies in repetition, day after day, over mats, shallows, and sunlit seas. They take carbon dioxide and water into living chemistry, and return oxygen to an Earth that is not ready to keep it in the air. The first importance of oxygen is not that it fills the atmosphere. For a long time, it does not. The early planet contains too many substances able to consume it. Dissolved iron in the oceans reacts with oxygen and falls out as iron minerals. Volcanic gases, reduced minerals in fresh crust, and chemical compounds in seawater all act as sinks, removing oxygen almost as soon as microbes produce it. This makes the early history of oxygen less like a sudden sunrise and more like water poured into a dry basin with hidden cracks. The basin must be filled, the cracks must be partly sealed, and only then can the level begin to rise. In the Archean, much of the oxygen released by photosynthetic microbes disappears into rock and water. Its absence from the atmosphere does not mean it is unimportant, it means its first effects are chemical and local. Around microbial mats, tiny zones of oxygen may form during daylight, then shrink at night or react with surrounding material. In shallow seas, oxygen can change the behavior of iron, sulfur, and organic matter, even if the wider atmosphere remains nearly oxygen-free. A waste product at the scale of a cell becomes a reagent at the scale of an environment. This is one of the most patient revolutions in Earth history. Oxygen is dangerous to many organisms that evolved without it, because it is reactive. It can damage cells and interfere with delicate chemistry. For anaerobic life, life that does not use oxygen, the rise of local oxygen is not a gift. It is a stress. Microbes living inside mats may retreat into lower layers, where oxygen is consumed before it reaches them. Others may evolve defenses against reactive oxygen compounds. Some lineages eventually learn to use oxygen's reactivity as a powerful tool for extracting energy, but that later advantage depends on a long period of adaptation. In the Archean, oxygenic photosynthesis therefore creates new ecological structure. The top of a mat may become oxygenated in sunlight while deeper layers remain reduced. Day and night produce chemical breathing in the sediment. Oxygen appears, reacts, fades, and appears again. The mat becomes a place where different metabolisms press against one another in extremely thin layers. What seems like green or dark slime on sediment is, in chemical terms, a living frontier. The connection between photosynthesis and carbon dioxide also changes the climate problem. Carbon dioxide is a greenhouse gas, and on the young Earth it helps compensate for the fainter sun. Photosynthetic organisms remove carbon dioxide as they build organic matter. If that organic carbon is quickly decomposed and returned to the environment, the climate effect may be limited, but if some of it is buried, then carbon can be stored away from the atmosphere and ocean for long periods. Oxygenic photosynthesis adds another layer, because the release of oxygen is tied to the burial of reduced carbon. For oxygen to accumulate permanently, not all the organic matter made by photosynthesis can be consumed again. Some must escape immediate recycling. Sediment, burial, and preservation therefore become part of the oxygen story. A microbial mat does not change the atmosphere by sunlight alone. It changes it through an entire chain carbon fixation, organic production, burial, reaction with minerals, and the slow saturation of oxygen sinks. The rock record preserves this story indirectly. Banded iron formations, with alternating layers rich in iron minerals and silica, become one of the great mineral witnesses of an ocean where dissolved iron and oxygen met under changing conditions. These deposits are not simple photographs of cyanobacteria at work, and their formation can involve several processes, but they show that the chemistry of the ocean was being reorganized around iron and oxidation. In an anoxic sea, iron can remain dissolved. Add oxygen, and iron can precipitate as solid minerals, settling to the seafloor in layers that later become stone. The scale of these formations suggests that the production, movement, and consumption of oxygen were no longer tiny curiosities. They were becoming part of the ocean's long-term chemistry. The air above may still have carried little oxygen, but the sea was recording encounters between microbial metabolism and planetary reservoirs of reduced material. The timing of oxygenic photosynthesis remains one of the careful questions in Archean science. Some evidence suggests that the biological machinery may have appeared well before oxygen accumulated in the atmosphere. Other interpretations are more cautious, because ancient rocks are altered and some chemical signatures can have more than one explanation. The safest story is not that the Archean atmosphere suddenly became breathable. It did not. Nor is it that cyanobacteria instantly transformed the planet once they appeared. They did not. The stronger story is slower and more interesting. A metabolism evolves that can use water as an electron source, opening access to an almost unlimited supply compared with more restricted reduced compounds. That metabolism spreads where light, nutrients, and tolerable conditions allow. Its waste product reacts with the world. For a long time, the world absorbs it. Then, as sinks are altered, buried, or overwhelmed, the balance begins to shift. The Archean contains the long preparation for that shift. Photosynthesis also changes the meaning of sunlight. Before biology, sunlight drives atmospheric and surface chemistry directly. After photosynthetic microbes spread, sunlight enters living systems, is stored in organic molecules, and passes through food webs too small to see. Microbes that do not photosynthesize can live on the products of those that do. Decomposers recycle organic matter. Methane-producing microbes may consume some of that material in oxygen-poor settings. releasing methane, another greenhouse gas. Other organisms may use sulfur, iron, or hydrogen in association with mat communities. The biosphere becomes metabolically layered, with sunlight at the surface and chemical exchange below. This does not create a modern ecosystem, but it creates a true microbial economy. Matter moves through living pathways before returning to water, sediment, or air. The planet's chemistry is no longer only geological chemistry with life added on top. It is increasingly a combined system, where living processes and non-living reservoirs push against one another. The visual change would still be subtle from a human distance. The continents are not green with plants. The sea is not filled with drifting algae in the later sense. Oxygen does not yet make the sky safe for animal lungs, and no animal lungs exist to test it. But in shallow water, microbial surfaces may expand across suitable settings, brightened or darkened by pigments that harvest light and protect cells from radiation. These pigments are practical molecules, yet they give the first living colour to parts of the planet's surface. In some places, mats grow over sediment. In others, cells live suspended in the upper ocean or attached to minerals. Each cell's oxygen release is vanishingly small. The cumulative effect is not. Across time spans longer than mountain ranges survive. A microscopic metabolism begins to alter the fate of iron, carbon, sulfur, methane, climate, and future life. It prepares the conditions for later oxygenation while creating stress for the older anaerobic world. The Archean does not end with oxygen triumphing. It ends with oxygen becoming unavoidable. This is the deeper consequence of photosynthesis. It turns life from a passenger in Earth's environments into a force able to change the limits of those environments. The same organisms that need the planet's warmth, water, and nutrients begin changing the atmosphere and ocean that support them. The waste of one age becomes the foundation and crisis of another. In the sections ahead, this chemical pressure begins to intersect with the motion of crust and the assembly of land masses, because the rise of oxygen cannot be separated from the rocks that consume it, the sediments that bury carbon, and the tectonic systems that keep exposing fresh material to the surface. Moving crust changes the Archean story from a surface history into a planetary circulation. By the Mesoarchean, Earth has cooled enough for parts of its outer shell to behave as recognizable crust, yet the planet is still warmer inside than it will be in later eons. That warmth matters because crust is not only a lid, it is also a participant in the movement of heat from the interior toward the surface. Where mantle material rises, it can melt and produce new volcanic rock. Where crust thickens, weakens, or becomes dense, parts of it may sink, drip, fold, or be buried deeply enough to melt again. The modern image of plate tectonics, with large rigid plates spreading from ocean ridges and descending in long subduction zones, may not yet describe the whole Archean Earth. The early system is probably messier, hotter, and more regional. But the important change is that the surface is no longer simply being renewed in place, it is beginning to travel. Rock formed in one environment can be carried into another. Oceanic crust can be altered by seawater, buried, heated, and transformed. Lighter crust can gather into more durable nuclei. Sediments laid down in shallow water can be folded into greenstone belts and preserved between harder blocks of ancient continental material. The planet is learning to move its surface through its interior, and that movement begins to shape every other story already underway. The oldest continental cores, later called cratons, do not appear all at once as finished continents. They grow by addition, collision, melting, thickening, and preservation. Around them, greenstone belts preserve sequences of volcanic and sedimentary rocks that speak of ancient sea floors, volcanic islands, basins, and shallow marine environments compressed into narrow zones by later deformation. Their name comes from the greenish minerals produced by alteration and metamorphism, but their deeper meaning is structural. They are the stitched and folded remains of mobile Archean landscapes, basaltic lava, volcanic ash, chemical sediments, banded iron layers, and fragments of early crust can all be caught in these belts. They show that Earth's surface has become divided into regions with different histories, some dominated by volcanic construction, others by sedimentation, others by deep burial and reworking. This division is essential for the growth of complexity. A uniform surface gives chemistry fewer pathways. A moving, broken, and recombined surface creates edges, basins, heat sources, nutrient flows, and long-lived crustal anchors. Tectonic motion also deepens the oxygen story. Fresh rock exposed at the surface reacts with the atmosphere and ocean. Reduced minerals consume oxygen. Weathering draws carbon dioxide into dissolved forms and eventually into sediments. Burial carries organic carbon away from immediate decay, allowing oxygen production to have a lasting effect. Volcanism returns gases from the interior, including carbon dioxide, sulfur compounds, and water vapor. No part of this cycle stands alone. Microbes release oxygen in sunlit environments, but rocks decide how much of it can survive. Sediments bury organic matter, but tectonics decides whether those sediments remain near the surface, are deeply buried, or are later uplifted and eroded. Continents supply nutrients to the sea, but their size, height, and chemical composition depend on crustal growth. The Mesoarchean therefore turns the biosphere into one actor inside a larger moving system. Life changes the chemistry of the surface, but tectonics controls many of the reservoirs that receive, erase, or preserve those changes. The making and breaking of early land masses also changes the shape of shallow seas. When crust gathers into larger blocks, coastlines lengthen and sedimentary basins develop around them. When those blocks fragment or shift, seaways open, volcanic arcs form, and old margins are buried or destroyed. Sea level itself is not simply a line on a shore. It depends on the volume of ocean water, the shape of ocean basins, the heat and thickness of oceanic crust, and the rise or sinking of continental fragments. In a warmer Archean Earth, oceanic crust may be thicker and more buoyant in some settings, affecting the amount of land exposed above the sea. The result is a changing map of islands, shallow platforms, volcanic ridges, and submerged basins. For microbial life, such motion matters at the scale of habitat. A mat that flourishes on a tidal flat may be drowned by subsidence, buried by ash, or uplifted and exposed. A basin rich in nutrients may become isolated, evaporative, or connected again to the open ocean. A hydrothermal system may fade as its heat source cools, while another opens along a new fracture. Tectonics does not simply rearrange continents, it rearranges opportunity. The question of when modern plate tectonics truly begins remains unsettled because the evidence is difficult and the definitions are strict. Some researchers look for signs of subduction, where one plate descends beneath another. Others look for paired metamorphic belts, changes in crustal composition, the formation of certain granitic rocks, or the assembly of stable cratonic roots. The Archean record offers hints, but not a single global switch. It may be more accurate to imagine a gradual transition from a stagnant or episodic early lid toward increasingly connected plate-like behavior. In some regions, slabs of dense crust may sink into the mantle. In others, hot mantle plumes may push upward, causing volcanic outpourings and crustal doming. In still others, thickened crust may collapse sideways or drip downward under its own weight. These processes can coexist. A young planet does not need to choose one tidy mode. Its heat flow is high, its lithosphere variable, and its surface continually modified by water. The motion of crust may be intermittent in one region and sustained in another. What matters for the Archean story is not whether every modern tectonic feature has appeared in its later form. What matters is that crust is no longer only a skin over the mantle. It is being cycled, differentiated, and assembled into long-lived pieces. The growth of continental roots is especially important. Beneath some Archean cratons, the mantle becomes chemically depleted and relatively buoyant, forming thick roots that help the overlying crust survive. These roots act like deep anchors. They make parts of the crust harder to destroy, allowing ancient terrains to persist while surrounding regions are reworked. Without such survival, the early record would be even thinner than it already is. Cratonic roots also affect topography, erosion, and the long-term stability of basins. A continent with a durable root can remain a platform for sedimentation, weathering, and shallow marine life across immense time. It can be broken at its edges, intruded by magma, and covered by seas, yet still retain an identity. This is the beginning of Earth's habit of keeping old cores inside younger continents. Much later, pieces of Archean crust will sit inside modern land masses, surrounded by rocks of many ages, like old foundations under a city rebuilt again and again. In the Mesoarchean, that habit is still forming. Tectonic recycling also affects the chemistry of the ocean. When seafloor is newly made and hot, it reacts strongly with seawater, removing some elements and adding others. When sediments are buried, they carry water, carbon, sulfur, iron, and organic matter into deeper crust. When rocks melt, some of those materials return in magmas and volcanic gases. This circulation can regulate climate over long spans by moving carbon between air, ocean, crust, and mantle. It can also influence nutrient supply, because weathering and volcanic activity release phosphorus, iron, nickel, and other elements important for microbial metabolism. Early life is constrained by what the planet makes available. A biosphere can only expand where energy and nutrients meet tolerable conditions. Tectonics changes that meeting place. It raises fresh rock into weathering zones. It creates basins where nutrients accumulate. It feeds hydrothermal systems that supply chemical energy. It buries organic matter and exposes old deposits again. The slow motion of crust becomes a hidden partner in microbial evolution. There is no single dramatic continent to mark this stage, no clean global map that can be drawn with confidence. Instead, the evidence points to a planet becoming more internally connected. Ancient crustal blocks grow and collide. Volcanic provinces spread across sea floors. Sediments collect in basins and are later compressed. Greenstone belts preserve fragments of lost environments. Continental roots thicken below some regions while other crust is recycled away. The surface becomes a mosaic of persistence and erasure. This mosaic is the condition in which the later Archean will unfold. It allows oxygen to react with fresh minerals, carbon to be buried in sediments, nutrients to enter shallow seas, and microbial ecosystems to follow shifting margins across deep time. By the end of this movement, Earth is not yet the plate tectonic planet of the Phanerozoic, with continents arranged in recognizable cycles of collision and breakup, but it is no longer a planet of isolated crustal patches alone. Its outer shell has begun to carry memory from place to place, down into heat and back toward light. The next question is what kind of climate can exist on such a world? where a faint young sun shines over moving crust. Volcanic gases rise into the air, microbes alter the chemistry of water. And greenhouse warmth must hold the oceans open without letting the planet drift beyond the limits of endurance. The Archean climate is held between two opposing facts that do not seem, at first, to belong together. The young sun shines with less energy than it will later provide, yet the surface of Earth remains warm enough for oceans to persist across immense stretches of time. Without some source of added warmth, a fainter sun could have left the planet locked in ice. Instead, the Archean carries liquid water, active weathering, and microbial habitats beneath an atmosphere very different from the one that later animals inherit. The solution lies not in one gas, one process, or one steady condition, but in a shifting balance among volcanic outgassing, ocean chemistry, weathering, methane production, carbon burial, and the slow growth of continents. Climate is already a planetary negotiation. Heat rises from the interior. Greenhouse gases trap some of the energy that would otherwise escape to space, and the ocean spreads that warmth across a surface where almost every reservoir is still changing. This makes the Archean climate both durable and unstable. It keeps water present, but it does so through a balance that can be disturbed from more than one direction. Carbon dioxide is one of the main stabilizing gases in this early atmosphere. Volcanoes release it from the interior, and weathering removes it when rain and seawater react with rock, carrying carbon into dissolved forms and minerals. On a planet with little exposed land, the rhythm of this removal differs from later Earth. Weathering still occurs on volcanic islands, early continental blocks, seafloor, and fresh impact or lava surfaces, but it lacks the plant roots, soils, and animal activity that later accelerate chemical breakdown. Bare rock reacts more directly and perhaps more slowly in some settings, yet the Archean supplies huge amounts of fresh basalt. And basalt can consume carbon dioxide efficiently when water moves through it. The balance between volcanic release and rock consumption helps regulate temperature over long time. If carbon dioxide rises, warming can increase rainfall and weathering, pulling some carbon back out of the air and ocean. If carbon dioxide falls, weathering may slow, allowing volcanic gases to rebuild the greenhouse. This feedback is not perfect. It works through geology, not intention, and its strength depends on land area, rock type, ocean chemistry, and heat flow. Methane adds a more uncertain and more delicate layer. In an oxygen-poor atmosphere, methane can survive far longer than it can today. It absorbs heat effectively, so even a modest amount can help warm the planet under the faint young sun. Some methane may come from geological sources, especially where water reacts with certain rocks to produce hydrogen, which can then participate in further chemical pathways. But as microbial ecosystems develop, methane-producing organisms may become an important source. These microbes, known as methanogens, do not use oxygen. They live by combining carbon dioxide with hydrogen or by processing simple organic compounds, releasing methane as a byproduct. In the Archean, such metabolism fits the world around it. The oceans and sediments contain low oxygen environments everywhere. Organic matter from photosynthetic or other microbial communities can settle into sediments. Hydrogen can be supplied by hydrothermal systems. The result is a climate connection between invisible cells and the whole atmosphere. Microbes too small to see may help warm the planet enough for their own habitats to persist. Yet methane is not simply a warmer blanket placed over the Earth. It is chemically vulnerable, especially to sunlight in the upper atmosphere. Ultraviolet radiation can break methane apart and drive reactions that produce organic haze. Such a haze may have cooled the planet by reflecting sunlight, even while methane itself warmed it. The climate effect depends on concentration, atmospheric chemistry, and the ratio of methane to carbon dioxide. Too little methane and the greenhouse weakens. Too much methane under certain conditions and a haze may form thick enough to reduce incoming light. This gives the Archean atmosphere a built-in tension. The gas that helps prevent freezing can also contribute to cooling if the chemical balance shifts. The sky itself may carry the sign of that tension, perhaps as a photochemical haze that softens the sunlight reaching the surface. Such a haze would not be merely atmospheric decoration. It would influence climate, surface chemistry, and the radiation environment experienced by shallow microbial communities. Oxygen begins to complicate this balance long before the atmosphere becomes oxygen-rich, as oxygenic photosynthesis spreads. Small amounts of oxygen react with methane and reduce its lifetime. Even tiny increases in available oxygen can weaken methane's greenhouse influence over time. At first, oxygen is consumed by iron, sulfur, volcanic gases, and reduced minerals. But local oxygenation near microbial mats and shallow waters can still affect surrounding chemistry. The climate system now contains a quiet conflict between different microbial metabolisms. Photosynthetic organisms remove carbon dioxide and release oxygen, methanogens, often in oxygen-free sediments and waters, release methane. Other microbes consume organic matter, sulfur compounds, iron, or hydrogen. Their activities do not simply make an ecosystem. They alter the gases that help decide whether Earth remains warm or begins to cool. The planet's climate becomes partly biological, while still being controlled by geology. It is a shared system, and no part of it has complete authority. The ocean helps buffer this system, but it also records its changes. Warm water affects the rate of reactions with crust. Dissolved carbon moves between atmosphere and sea. Iron remains mobile where oxygen is scarce, and precipitates where oxidation becomes important. Organic matter can be recycled by microbes or buried in sediment. Burial matters because it separates carbon from immediate return to the atmosphere. If organic carbon is buried, oxygen produced by photosynthesis has a better chance of accumulating somewhere, even if only in local environments at first. If that carbon is decomposed instead, carbon dioxide and methane may return to the system. Sedimentary basins, therefore, become climate machinery. They are not just places where mud and chemical precipitates settle. They are storage sites for carbon, iron, sulfur, and the chemical consequences of life. Tectonics controls how many of these basins form, how long they last, and whether their contents are buried deeply or later exposed again. The climate depends on the architecture of the crust as much as on the gases above it. During parts of the Archean, surface temperatures may have been warmer than most modern environments, though estimates vary widely because the evidence is indirect and altered. Some minerals and isotopic patterns suggest warm oceans. Other interpretations allow more moderate conditions. The uncertainty itself is important. A single global number cannot capture a world with volcanic regions, shallow basins, deep seas, hydrothermal circulation, and changing atmospheric composition. What can be said more safely is that Earth avoids permanent global freezing for much of the Archean despite a fainter sun. It does so through greenhouse warming, internal heat, and feedbacks between rock, water, air, and life. This success is not guaranteed from moment to moment. It is maintained by reservoirs that can be pushed out of balance. A major decline in methane, a drawdown of carbon dioxide, increased weathering, changes in volcanic gas release, or the spread of oxygen-producing microbes could all move climate toward cooler conditions. The Archean climate is therefore not simply hot, it is sensitive. That sensitivity prepares the way for the first evidence of ice. As microbes expand and as crustal processes continue to alter carbon dioxide, the greenhouse blanket may thin in certain intervals. If methane falls because oxygen or other chemical changes shorten its lifetime, a world warmed by methane can cool quickly by geological standards. If carbon dioxide is drawn down through weathering and burial, the same direction becomes stronger. A planet that has remained warm under a faint sun can begin to cross thresholds where high latitudes freeze, where ice forms seasonally or regionally, and where the rock record begins to carry glacial traces. The movement from warmth toward ice is not a contradiction. It is the consequence of a climate system finally complex enough to be unsettled by its own success. Life helps stabilize habitats, then alters the air. Crust creates land and basins, then draws down greenhouse gases. Oceans preserve warmth, then record cooling. By the close of this stage, the Archean world still holds broad seas beneath an alien sky. But the balance that kept those waters warm is no longer beyond challenge. In the next movement, the first glacial signals appear like a colder edge to the same story, showing that even on a young planet rich in internal heat and greenhouse gases, the climate can bend far enough for ice to enter the record. The first glacial signals of the Archean do not arrive as a complete frozen planet. They arrive as a warning written into stone, a sign that Earth's early warmth could weaken enough for ice to become part of the surface system. For much of the Archean, the planet seems to have solved the faint young sun problem through greenhouse gases and internal heat, keeping oceans liquid beneath a sky with almost no free oxygen. Yet the same world that preserves warm seas also begins to preserve hints of cold. In ancient sedimentary sequences, some rocks appear to record the movement of ice or the presence of cold climate deposits, though the evidence is difficult because the rocks are very old, altered, and often displaced from their original latitudes. A glacial deposit is never just a temperature reading. It is a record of ice thick enough to scrape, carry, drop, or disturb sediment. To recognize it in Archean rocks, geologists look for mixtures of grain sizes, striated surfaces, drop stones, and other features that may indicate ice rather than ordinary mud flows, volcanic debris, or submarine landslides. The interpretation must be cautious, but the implication is profound. A planet still young, still volcanically active, still wrapped in greenhouse gases, may nevertheless have cooled enough for ice to reach across parts of its surface. That possibility changes the emotional temperature of the Archean story. The Eon is often imagined as relentlessly hot, a world of volcanic seas, dense air, and warm oceans coloured by iron and shadow. But the rock record suggests a more unstable climate. Warmth remains dominant in many intervals, yet it is not invulnerable. As the biosphere grows and the crust becomes more effective at cycling gases, the greenhouse balance can shift. Carbon dioxide can be drawn down through weathering and burial. Methane can be weakened by changes in atmospheric chemistry, especially as oxygen begins to appear locally and gradually becomes harder for the planet to absorb completely. A methane-rich atmosphere may warm the world strongly, but it also depends on low oxygen and a delicate photochemical balance. If methane falls, the greenhouse effect can shrink. If organic haze thickens, sunlight can be reflected away. If continental weathering increases as landmasses grow, carbon dioxide removal can intensify. None of these changes needs to freeze the whole planet at once. They only need to push some regions, perhaps high latitudes or elevated surfaces, past the threshold where snow survives and ice begins to move. The first ice, therefore, belongs to a system, not a single cause. It may reflect biology, geology, atmosphere, and ocean acting together. Oxygen-producing microbes can change atmospheric chemistry, but they do not act alone. They require nutrients supplied by weathering and hydrothermal systems. Their carbon can affect climate only if some organic matter is buried. Weathering removes carbon dioxide only where fresh rock, water, and exposure allow it. Tectonics creates land and basins, but volcanism returns greenhouse gases from below. The climate cools when these processes lean in one direction for long enough. The Archean's first glacial hints are important because they show that Earth is no longer merely escaping its molten beginning. It is entering a mode of climate variability, where feedbacks can build toward major environmental consequences. The planet has become complex enough to surprise itself. Ice, when it forms, alters the planet in ways warmth does not. It brightens the surface, reflecting sunlight and encouraging further cooling. It stores water temporarily on land or across shallow seas. It grinds rock into fine sediment, exposing fresh mineral surfaces that can later react with the atmosphere and ocean. It changes sea level if enough water is locked away. It affects the supply of nutrients to marine environments when glaciers advance, retreat, and release ground rock into the water. Even limited glaciation can reshape the chemistry of nearby seas. A glacier is not merely cold water made solid, it is moving geology. It carries fragments of the land, scrapes the surface below, and leaves deposits that may outlast the climate that formed them. In the Archean, such deposits become rare clues to a planetary system that has crossed into a colder state, at least regionally. Yet there is uncertainty in every direction. The positions of ancient continents are difficult to reconstruct. A deposit that now sits in one place may have formed far away. Rocks that seem glacial may have been modified by later deformation. Some features can be produced by underwater gravity flows or volcanic processes. The older the record, the more each interpretation must compete with alternatives. This uncertainty does not erase the possibility of Archean ice. It makes the evidence more valuable, because each preserved clue has survived a world almost designed to destroy it. The question is not only whether ice formed, but what kind of Earth allowed its trace to remain. If a glacial deposit is real, then somewhere a landscape was cold enough, a basin was positioned correctly, sediment was delivered and preserved, and later tectonic history failed to erase the message completely. A small survival becomes a large constraint. It tells the climate story to stay open, not to settle too easily into permanent heat. For microbial life, cooling introduces both stress and opportunity. A colder climate can reduce the range of habitable surface waters, alter chemical reaction rates, and change the distribution of nutrients. Ice can block sunlight from water beneath it, threatening photosynthetic communities. But ice can also create protected liquid environments below or within frozen margins. Shielded from ultraviolet radiation and buffered against rapid atmospheric changes, seasonal freeze and thaw can concentrate salts and organic molecules. Glacial grinding can deliver finely powdered minerals into oceans, perhaps fertilizing microbial ecosystems after retreat. Life in the Archean is still microbial and flexible, living across chemical gradients rather than depending on narrow animal requirements. Some communities may retreat into sediments, hydrothermal systems, deeper waters, or sheltered basins during colder intervals. Others may flourish when ice recedes and nutrients pulse into shallow seas. The biosphere is not separate from climate. It is pressed by climate, and it also helps shape the conditions that climate responds to. The deeper meaning of early glaciation lies in feedback. If photosynthesis reduces carbon dioxide through organic burial and contributes oxygen that weakens methane, then life can cool its own world if cooling spreads ice. Weathering may slow under frozen cover, allowing volcanic carbon dioxide to build again. If ice retreats, fresh rock is exposed. Weathering can accelerate, and nutrients can enter the sea. These loops are not simple or perfectly balanced. They operate over spans too long for any living creature to sense, through reservoirs larger than any ecosystem. But they reveal that Earth has entered the kind of planetary behaviour that will define later eons. Climate moves through thresholds. The biosphere responds and contributes. The crust stores and releases. The atmosphere records the changing mixture. The ocean transmits the consequences. The Archean ice signals are early evidence of this connectedness. They show that even before animals, before plants, before oxygen fills the air, the planet already has the capacity for global-scale environmental change. This does not mean the Archean becomes an ice world in the familiar later sense. The cold intervals, if preserved correctly, are likely part of a larger pattern of fluctuation. Warmth returns, volcanic gases continue to rise, methane may be rebuilt in low oxygen settings, the ice retreats or vanishes from the preserved record. Oceans remain central, microbial ecosystems continue. But after the first glacial signals, Earth can no longer be imagined as climate stable simply because it is young. The Eon contains both heat and cold, both greenhouse intensity and the first hard evidence that the balance can tip. In that tipping, a new kind of planetary drama appears, though it remains quiet and slow. The world that began as molten rock and bombardment has become a world where invisible cells, moving crust, atmospheric chemistry, and sunlight can help decide whether ice gathers at the edges of the sea. The next stage follows the biosphere after such thresholds, as microbial life expands through the later Archean not as a fragile accident, but as an increasingly widespread presence across marine surfaces, sediments, and perhaps even the first exposed lands. After the first glacial signals fade from the record, the later Archean does not return to an earlier simplicity. The planet has changed too much for that. Continents have begun to gather into more durable pieces. Shallow seas have become recurring habitats rather than rare accidents, and microbial life has already shown that it can leave patterns in sediment, alter chemistry, and survive through environmental disturbance. In the Neo-Archean, life is still microscopic, still without animals, plants, fungi, or visible bodies, yet it is no longer best imagined as a fragile experiment confined to a few hidden refuges. It has become a broad planetary presence, distributed across marine basins, tidal flats, sediments, hydrothermal systems, and perhaps exposed wet surfaces on land. The biosphere remains thin compared with later ages, but thin does not mean weak. A microbial film can be only a slight covering over mud or rock, and still change how minerals form, how sediment is trapped, and how gases move between ocean and air. The later Archean is therefore an age of expansion without spectacle. Life spreads not by becoming large, but by becoming repeated. In shallow marine settings, microbial mats likely form some of the most important living landscapes on Earth. They occupy places where sunlight reaches sediment and where water movement brings dissolved nutrients without always tearing the community apart. These mats can be layered internally, with oxygen-producing microbes near the light, other organisms below them living in lower oxygen or oxygen-free zones, and still others using sulfur, iron, hydrogen, methane, or organic matter produced by neighbours. Their structure is not random. It follows chemical need. Light declines downward. Oxygen appears and disappears with the day. Waste from one group becomes fuel for another. The mat becomes an ecosystem compressed into a skin. In the Neo-Archean, such systems may become more widespread as suitable coastlines. Platforms and shallow basins develop around growing crustal blocks. Each habitat is local, but the pattern is global in its implications. Wherever similar conditions appear, similar microbial strategies can take hold. The biosphere begins to occupy Earth through repetition of environments, rather than through the spread of large organisms. Open oceans may also contain microbial life, though the evidence is harder to preserve. Cells suspended in the upper water can harvest sunlight or use dissolved chemical energy, then sink, decompose, or become part of the sedimentary record only indirectly. In a world without planktonic animals, shells, or large grazers, the ocean's living structure would be almost entirely microbial. Organic particles may fall slowly through the water, feeding communities below. Some carbon returns quickly to dissolved form, some is buried, some becomes available to methane-producing microbes in sediments where oxygen does not reach. The sea is not crowded in a visible way, yet it is increasingly processed by life. Dissolved carbon, iron, sulfur, nitrogen, and phosphorus pass through living pathways before returning to the wider environment. The ocean remains chemically Archean, rich in reduced materials and poor in free oxygen, but it is no longer only a chemical reservoir. It is a biological circulation system at microscopic scale. The possible move onto exposed land is more subtle and more uncertain, but it carries a striking implication. Long before roots, mosses, lichens, or soils in the later sense, microbial communities may have colonized wet rock surfaces, damp sediment, spring margins, and periodically flooded flats. They would not form forests or even true ground cover as later eyes understand it. They would form films, crusts, and mats, sometimes dark, sometimes greenish or brownish, depending on pigments and minerals. These communities would be vulnerable to drying, ultraviolet light, burial, erosion, and chemical stress. But microbes are able to live inside pores, under thin mineral layers, within salt crusts, or beneath translucent grains that admit light while offering protection. On Archean land, even scattered microbial films could begin to alter weathering. They could trap dust, retain moisture, produce organic acids, and influence the formation of thin surface crusts. This is not soil yet in the full biological sense, but it may be a first step toward biologically modified ground. The barren continents would not remain chemically untouched once life reached their damp edges. Such expansion does not happen as a single advance. It is patchy, reversible, and tied to water. A microbial community on a tidal flat may flourish during stable conditions, then be buried by sediment or removed by waves. A wet volcanic surface may support life only while groundwater seeps across it. A hot spring may host dense communities along its cooler margins but become sterile closer to the source. An exposed rock face may carry cells in protected cracks rather than across open surfaces. The later Archean biosphere is therefore not a smooth blanket over the planet. It is a network of occupied thresholds, light and sediment, water and air, heat and chemistry, rock and atmosphere. This patchiness matters because it prevents the story from becoming too simple. Life expands, but it remains dependent on microenvironments. It changes the planet, but only through countless local actions. Its power lies in the number of places where small changes can accumulate. The diversification of microbial metabolism is one of the deeper forces behind this expansion. Oxygenic photosynthesis is important, but it is not the only pathway shaping the world. Methanogens produce methane in low oxygen settings, influencing greenhouse warmth. Sulfur-using microbes transform sulfur compounds near vents, sediments, and stratified waters. Iron-related metabolisms may interact with dissolved iron and contribute to mineral formation or alteration. Fermenting organisms break down organic material where other electron acceptors are scarce. Some microbes may live on hydrogen generated by reactions between water and rock. The details of early evolutionary relationships are difficult to reconstruct because genes evolve, transfer, and vanish over billions of years, while rocks preserve only indirect traces. But the broad point remains: the Archean biosphere becomes metabolically varied. It is not a single kind of microbe doing a single kind of work. It is a set of communities partitioning energy sources across the planet's chemical landscape. This metabolic variety gives life resilience. If one environment changes, another may remain open. If oxygen appears locally, anaerobic organisms can retreat into deeper layers. If organic matter accumulates, decomposers and methane producers can use it. If hydrothermal fluids supply hydrogen or sulfur, specialized communities can gather there. If sunlight reaches shallow sediment, photosynthetic mats can spread. A world with many metabolisms can survive instability better than a world dependent on one pathway. The Neo-Archean biosphere is still simple compared with later ecosystems, but it is not primitive in the sense of being ineffective. It is adapted to a planet of chemical contrasts. Its communities fit into gradients with a precision that later large organisms will never fully replace. Even after animals evolve, microbes will remain Earth's deepest and most persistent form of life. In the Archean, that truth is already being established. The rise of widespread microbial surfaces also affects sedimentary records. Mats can stabilize loose grains, allowing fine layers to form in places where currents might otherwise disturb them. They can create wrinkle structures, laminated fabrics, and mineralized textures that later become clues to biological activity. They can influence the precipitation of carbonates, silica, sulfides, and iron minerals. They can create small oxygenated pockets where certain reactions occur, even while surrounding waters remain anoxic. Some organic matter becomes trapped and buried, contributing to the long carbon cycle. These changes do not announce themselves instantly in the atmosphere, but they alter the terms under which later oxygen accumulation becomes possible. Each buried layer of reduced carbon, each iron deposit shaped by oxidation, each microbial surface that processes carbon dioxide and releases oxygen, contributes to the gradual filling of Earth's chemical sinks. The biosphere is preparing a planetary transition without yet completing it. The Neo-Archean landscape therefore carries two realities at once. From a distance, Earth may still look like an ocean-dominated, volcanic, oxygen-poor world, with scattered landmasses under a hazy sky and no visible organisms larger than microbial films. Up close, suitable surfaces are alive in ways that matter deeply. Shallow sea floors can be patterned by mats, sediments can be bound by cells, springs and vents can host chemical communities, damp exposed rock may carry early biological crusts. The planet is still largely austere, but it is no longer merely geological. The boundary between living and non-living surface processes has become harder to separate. The next shift will place this expanding biosphere against larger continental organization, as Archean land masses assemble into a scale that begins to resemble a supercontinent, and as oxygen production continues to press against the vast reduced reservoirs of the planet. Kenolon belongs to the Archean as both a landmass and an argument. It is reconstructed from fragments that now lie far apart, from ancient cratons, greenstone belts, magnetic clues, and matching histories of crustal growth and deformation. No one can walk its coastline in the record as a complete outline. No single map can be drawn without uncertainty. Yet the evidence suggests that by the Neo-Archean, pieces of Earth's early continental crust had begun assembling into a larger structure, a scale of land that begins to deserve the name supercontinent. This does not mean a world of broad, fertile interiors, river valleys lined with vegetation, or mountains clothed in soil. Kenneland would have been stark, mineral, and largely silent, a gathering of old crustal blocks under an oxygen-poor sky. Its surfaces were raw rock, volcanic plains, sedimentary basins, shallow seas, and eroding margins. But its assembly matters because continents change the planet even when they are lifeless to the eye. A larger landmass increases the area where rock can meet rain, air, and sunlight. It changes sea level patterns, creates new basins, alters currents, supplies nutrients to coastal waters, and affects the burial of carbon. In the late Archean, land is not a backdrop, it is machinery, and Kennerland may represent one of the first times that machinery operates at truly planetary scale. The assembly of such a landmass depends on tectonic behaviour that has become more organised than the scattered crustal survival of earlier time. Ancient blocks collide, volcanic arcs are added, sediments are squeezed and heated, and deep roots strengthen under cratons that can persist across billions of years. The process is not smooth, and it may not resemble modern supercontinent assembly in every detail. The Archean mantle is still hot, the lithosphere may behave unevenly, and different regions may move by different styles of deformation. Still, the result is clear enough in outline. Earth is producing continental nuclei large and stable enough to gather into a major configuration. Around their margins, shallow marine platforms and sedimentary basins become increasingly important. These are the places where microbial mats spread. Organic carbon can be buried, and iron, silica, sulfur, and carbonate minerals can accumulate in layered records. A supercontinent is therefore not only a piece of geography, it is a way of reorganizing chemical exchange. When land grows and assembles, the ocean receives different supplies, weathering changes, nutrient delivery changes, the balance between exposed rock and submerged crust changes. Even the atmosphere becomes tied to the new shape of the surface, because gases are consumed and released through reactions that depend on where rock, water, and air are allowed to meet. Oxygen sits at the centre of this unfinished transformation. By the Neo-Archean, oxygen-producing microbes are likely an established part of many sunlit environments, but the atmosphere remains far from breathable. The reason is not that oxygen production is trivial. It is that the planet contains immense chemical reservoirs able to absorb oxygen before it can accumulate freely. Dissolved iron in the oceans reacts with it. Reduced minerals in volcanic rock consume it. Gases from the mantle react with it. Organic matter, if not buried, uses it during decay. The young biosphere pours a reactive waste product into a world built from materials that have not yet been oxidized. For a long time, the world takes that oxygen away. Yet this removal is not the same as no change. Each reaction alters a reservoir. Iron that once remained dissolved becomes mineral. Reduced surfaces become oxidized. Sediments store new chemical information. The system is being prepared, sink by sink, layer by layer, for a later atmospheric shift. The late Archean is therefore an age when oxygen is important not because it has won, but because it is beginning to force the planet to spend its old capacity to hide it. Banded iron formations are among the most visible signs of this struggle. Their alternating layers of iron-rich minerals and silica speak of an ocean in which iron and oxidation repeatedly meet, though the exact mechanisms can vary from place to place and through time. They are not simple oxygen meters, but they are records of a world where dissolved iron is being removed on an enormous scale. Microbial activity may contribute by producing oxygen in surface waters, while ocean circulation, hydrothermal input, and chemical conditions determine where and how minerals settle. In such deposits, biology and geology cannot be separated cleanly. Life supplies a new chemical pressure. The ocean supplies iron, the crust supplies basins, tectonics controls preservation. When these conditions align, The result is layered stone that carries the memory of an ocean, unlike the modern one. The significance is cumulative. Every iron layer formed through oxidation represents oxygen that did not remain in the air. Every buried organic layer represents carbon held away from immediate recycling. Every weathered surface represents another place where atmospheric and ocean chemistry have reacted with rock. The rise of oxygen is not a single upward line. It is a long contest among production, consumption, burial, and release. Kennerland may influence that contest by changing the scale and arrangement of weathering and sedimentation. Larger continental masses can create extended coastlines and broad shelves where microbial communities thrive in shallow sunlight. They can feed phosphorus and other nutrients into nearby seas, supporting productivity. They can generate basins where organic matter is buried deeply enough to avoid rapid decomposition. They can also expose large volumes of fresh rock to weathering, consuming carbon dioxide and sometimes oxygen, depending on mineral chemistry. Thus, the same continental growth that helps microbial ecosystems expand can also draw down greenhouse gases and absorb oxygen through exposed reduced materials. The result is not a simple push toward oxygenation. It is a rearrangement of the entire surface system. A larger landmass makes some oxygen accumulation more possible by encouraging organic burial. Yet it also gives the planet more rock with which to react. It increases the reach of biology while strengthening some geological sinks. The transformation remains unfinished because the processes that create oxygen also create new ways to delay its rise. Climate responds to this late Archean reorganization. Weathering of growing continents can remove carbon dioxide. Oxygen can shorten methane's lifetime, weakening an important greenhouse gas in an atmosphere where methane may have helped keep the planet warm under the fainter sun. Organic haze may form or thin depending on methane and carbon dioxide levels. Glacial episodes or cool intervals may become more likely when greenhouse support weakens, though volcanic outgassing can rebuild warmth over long spans. The climate system becomes sensitive to the same processes that control oxygen microbial production, carbon burial, tectonic exposure, volcanic release, and ocean chemistry. Kennerland's existence may amplify this sensitivity by giving Earth a larger and more durable land surface through which weathering and erosion can operate. If rivers and runoff carry nutrients into the sea, productivity may rise. If productivity rises and burial follows, oxygen has a better chance to escape its immediate sinks. If greenhouse gases decline too far, ice can return, changing weathering, sea level, and nutrient supply again. The planet is entering a more tangled state, one in which life and geology become harder to assign to separate causes. The living surface of this world remains almost invisible from a distance. A traveller looking across Kennerland would not see forests or even low plants. The land would not smell of soil or leaf decay. No insects cross the shoreline. No animals disturb the sediment. Yet microbial films may occupy damp places, spring margins, tidal flats, and protected surfaces. Along the coasts, mats and stromatolites may pattern shallow waters. In sediments, oxygen-poor layers host organisms that produce methane or transform sulfur and iron. In the upper layers of mats, photosynthetic microbes release oxygen into tiny local zones before the surrounding world consumes it. This creates a planet with microscopic contrasts sharper than its barren appearance suggests. A mat only a little thicker than a film can contain oxygenated and anoxic zones. A shallow basin can switch chemistry between day and night. A continental margin can receive nutrients from weathered land, while also burying carbon in quiet sediment. The late Archean surface is austere, but it is chemically alive in a profound way. Its most important activity occurs in thin layers and slow reactions, not in visible movement. By the close of this stage, Earth has not yet crossed into the oxygen-rich world that will later reshape evolution. The air remains dangerous to animals that do not yet exist. The oceans remain unlike modern oxygenated seas. Reduced minerals and volcanic gases still hold enormous power over the atmosphere, but the direction of change is increasingly difficult to reverse completely. Continents have grown larger, microbial ecosystems have spread wider, oxygen production has become persistent, iron and carbon are being buried in records that will survive as testimony. Kenneland stands in this story as a sign that Earth's surface has gained scale. And with scale comes consequence. The planet is no longer only preserving fragments of habitability, it is assembling systems large enough to alter the balance of the atmosphere and ocean. The transformation is unfinished, but unfinished does not mean uncertain in its importance. It means that the last Archean Earth is poised between an older, reduced world and the first approach of a more oxidized one. The final movement of the Eon will gather these threads together, showing how oceans, continents, climate, microbes, and oxygen leave the Archean not as a completed Earth, but as a planet prepared for deeper upheaval. The Archean ends without becoming modern. That is the first thing its legacy requires. By around 2.5 billion years ago, Earth has oceans that have endured through bombardment, volcanism, chemical upheaval, and climate instability. But those oceans are still not the oxygenated waters of later ages. It has continents, or at least continental cores gathered into larger bodies. But those lands are still raw and mostly barren, lacking forests, soils, animals, and the green surface that will one day make dry land feel alive from a distance. It has life, but that life remains microbial, organized in films, mats, sediments, vents, and shallow seas. It has oxygen production, but not yet an atmosphere that can hold oxygen freely. The Eon closes as a world of thresholds, not completions. Almost every major system needed for the later living planet is present in some early form, and almost none has reached its later condition. The planet is no longer the nearly hidden Earth of the Hadean, whose rocks were almost entirely erased, but it is still an Earth whose most important work happens quietly, below familiar scales, in mineral reactions, buried carbon, microbial metabolism, and the patient assembly of continental roots. To understand what the Archean leaves behind, the oceans have to be seen not only as places where life survives, but as records of a chemistry in transition. For hundreds of millions of years, seawater interacts with volcanic crust, hydrothermal systems, early continental margins, and an atmosphere poor in free oxygen. Dissolved iron remains abundant in many settings, waiting for contact with oxygen or other oxidizing pathways that can turn it into mineral layers. Silica accumulates without the later biological demand from organisms that build shells. Carbon moves between air, water, microbes, and sediment. Sulfur cycles through volcanic gases, ocean chemistry, and microbial metabolism. The ocean is not a stable container holding life inside it. It is a reactive body, changed by everything that enters it and changing everything it touches. By the end of the Archean, the sea has already begun to register the pressure of oxygenic photosynthesis. Yet it still belongs to an older, reduced world. This tension will not vanish at the boundary. It will pass forward into the Proterozoic, where oxygen's slow rise will reorganize the ocean and atmosphere more deeply than the Archean alone allowed. The continents also carry a legacy of unfinished growth. Earlier fragments of stable crust have become more durable cratons, and those cratons hold within them the oldest surviving memories of the planet's surface. They preserve greenstone belts, sedimentary basins, ancient volcanic rocks, banded iron formations and altered remains of environments where microbes may have flourished. They also preserve absence. So much of the early Earth is gone that every surviving block is surrounded by silence. Yet that silence has meaning. It shows how dynamic the planet has been, how much crust has been consumed, melted, buried, or transformed beyond recognition. The Archean teaches that Earth's memory is selective, not because the past was empty, but because the planet is active. The same tectonic circulation that destroys evidence also builds the conditions that make long-term habitability possible. It recycles carbon, supplies nutrients, generates continents, buries organic matter, and exposes fresh rock to weathering. Destruction and preservation are not opposites here. They are coupled parts of the same planetary behaviour. The biosphere that leaves the Archean is small in body but large in consequence. Microbes have become sediment builders, chemical engineers, and atmospheric agents without ever becoming visible in the familiar way. They have formed mats in shallow waters, influence mineral precipitation, trapped sediment, and perhaps spread onto damp land surfaces. Some have used sunlight without producing oxygen. Others have learned the more disruptive pathway that splits water and releases oxygen. Still others have made methane, transformed sulfur, processed iron, fermented organic matter, or lived on chemical energy from rock and water. This variety is one of the Archean's deepest achievements. Life is no longer a single fragile possibility. It is a network of strategies matched to the planet's gradients. Wherever there is light, chemistry, heat, sediment, or protected water, microbes may find a way to live. This does not make the surface lush. It makes it biologically persistent. The world remains visually austere, but its chemistry is increasingly routed through living systems. The legacy of oxygen is more complicated than a simple rise. In the Archean, oxygen is produced and then consumed, generated locally and removed globally. Present in mats and shallow waters, but mostly absent from the wider air. Its first story is one of resistance. Iron, sulfur, volcanic gases, fresh basalt, and organic decay all take oxygen away before it can accumulate. But resistance changes the things that resist. Iron is buried as mineral. Reduced rocks become altered. Carbon is stored in sediments when organic matter escapes decay. Each reaction spends part of the planet's old chemical capacity. By the end of the Eon, oxygen has not conquered the atmosphere, but the old world has been forced to absorb its presence for a very long time. That prolonged absorption prepares the later Great Oxidation event, not as a sudden miracle, but as the outcome of deep preparation. The Archean makes oxygen unavoidable before it makes oxygen abundant. Climate carries the same pattern of preparation. Earth begins the Eon under the pressure of a fainter sun, heavy impact inheritance, volcanic outgassing, and greenhouse gases strong enough to keep liquid water present. It does not remain in one simple warm state. Methane, carbon dioxide, weathering, organic burial, oxygen production, and continental growth all push climate in different directions. The first glacial signals show that the system can cool. Warm intervals show that greenhouse recovery and internal cycling remain powerful. The planet is learning to swing, to respond, to cross thresholds and return. This matters because later Earth will be defined by such climate movement ice ages, greenhouse worlds, oxygen shifts, biological radiations, extinctions, and recoveries. The Archean is where that style of planetary behaviour becomes visible in its first forms. Climate is no longer only the consequence of the sun and volcanoes. It is increasingly tied to life, rock, ocean, and air in a single slow conversation. The transition into the Proterozoic is therefore not a curtain closing on one finished era and opening onto another. It is a change in emphasis. The Archean supplies the materials, the metabolisms, the continents, and the chemical tensions. The Proterozoic will inherit them and carry them into larger consequences. Oxygen will begin to gather more openly. The atmosphere will change. Oceans will stratify in new ways. Continents will assemble and break again. Microbial ecosystems will continue to dominate, but the conditions for more complex cells will slowly become possible. None of that future is obvious from the surface of late Archean Earth. There are still no animals moving through water, no plants reshaping land, no fungi threading through soil, no large bodies leaving tracks. Yet the absence of those later forms should not make the Eon feel incomplete in a lesser sense. The Archean performs the foundational work. It turns Earth into a planet with persistent oceans, enduring crust, active recycling, microbial life, biological energy capture, oxygen production, carbon burial, climate feedback, and geological memory. These are not decorations around the story of life. They are the deep structure beneath it. What remains most striking is the scale difference between cause and consequence. A microbial cell releases oxygen as waste, and the planet spends hundreds of millions of years absorbing it. A thin mat traps sediment, and the rock record gains a new kind of biological texture. A fragment of buoyant crust survives recycling, and a continent begins to grow around it. A molecule of methane warms the air until oxygen begins to shorten its life. A grain of zircon holds a memory older than almost every landscape around it. The Archean is built from such differences. Small forms act across enormous time. Local reactions become global pressure. Fragile evidence becomes the only doorway into vanished worlds. The Eon closes with no dramatic final scene, because deep time rarely ends its chapters that way. It closes with systems still in motion, oceans reacting, crust assembling, microbes spreading, oxygen pressing against ancient sinks, climate balancing between warmth and ice. The Earth that leaves the Archean is not yet familiar, but it is recognizably on the path toward the living planet. Its future complexity is not guaranteed in every detail, yet the necessary foundations have gathered. The story that began with a battered young world now reaches a quieter but more powerful condition. Earth has become a planet that can remember, react, and be changed by life. The Archean leaves behind a quiet kind of enormity. It does not leave a world that looks complete, and it does not offer a simple beginning that can be held in one image. It leaves fragments of crust, layers of altered stone, chemical traces, microbial structures, and the slow evidence of a planet learning how to endure its own changes. The oceans remain dark with ancient chemistry. The air remains poor in oxygen. The continents remain bare and mineral, without forests or animals or soil in the later sense. Yet beneath that unfamiliar surface, the essential movements have begun. Rock can survive long enough to remember. Water can remain long enough to shape. Life can persist long enough to alter the conditions around it. Oxygen can be made, even before it can gather. Climate can warm, cool, recover, and shift under the combined pressure of gases, weathering, burial, and light. What feels empty from a distance is active in detail. Microbes spread across sediment. Minerals change in the presence of waste from living cells. Basins receive carbon and iron. Continental roots thicken in the deep. The planet is still far from the later Earth, but it is no longer only young. It has acquired history. The next eon will carry that history into wider transformation, but the Archean remains the long foundation beneath it, the interval when Earth became a place where life was not merely possible, but established. Its record is broken, yet its meaning is steady. From heat, bombardment, water, stone, and microscopic persistence, the living planet begins to take form, slowly and without witness, under skies that have vanished from the world they helped create.